Let me search for your name. Oh, okay.
Also make me the co-host and.
Oh, yes. Okay. All right, cool.
Tom, we wanted to have a little introduction. So do you mind if I share the screen? Oh.
Sure. So I should unshare, that's what you're saying?
Yeah.
Yes. All right. So I will let everyone pile in, but I'm going to start off with an introduction to introduce our second keynote talk that we have by Professor Thomas Diederich from Oregon State University. And his talk will be is titled Machine Learning and Computational Sustainability Lessons Learned and Future Challenges. Dr. Diederich is a professor emeritus in the School of Electrical Engineering and Computer Science at Oregon State University. And Diederich has served as a co-PI and assistant director of the Institute for Computational Sustainability, which has led the 2 NSF expedition grants in computational sustainability. And he has supervised or co-supervised several postdocs and PhD students in this area, including Rebecca Hutchinson from OSU, Dan Sheldon from University of Massachusetts, Mark Crowley, Waterloo, Yan Dugarden, INRA, Jonathan Ferrier from Cicero, Liping Liu from Tufts, Sean McGregor, X Prize, Mahir Al-Kay from eCentier, and Kim Hall from OSU, Tadesse Zemichael from NVIDIA, and Amelia Snyder, the World Resources Institute. So without further ado, let's have Professor Thomas Diederich take it away.
Well, it's very exciting for me to attend this and see how the field of computational sustainability is developing and blossoming. I really love the morning talks and look forward to the afternoon ones as well, and tomorrow. So back in 2007, 2008, when Carla Gomez and I were first putting together the grant proposal for computational sustainability, I was giving talks, sort of putting forward a general model of what were the computational and machine learning challenges in computational sustainability. And I thought it would be interesting, maybe revealing, to sort of go back and look at what I was saying in those talks and update them with what our experience has actually been. So so this is a kind of a summative talk to try to look at where was computation the main issue and where were other problems came up. So of course, this is collaboration with many people. I'll just mention John Selker, who leads the TAHMO project that I'll discuss in a moment. Dan Sheldon, who was a postdoc with me and of course now is an associate professor at UMass. And Joe Albers, who's a professor in applied economics at the University of Wyoming. And I'll list all the various graduate students as we come along. So let's see. Keyboard focus. So this was the kind of diagram that I've been using now for 15 years. So Carla put forward this definition that computational sustainability is the study of computational methods that can contribute to the sustainable management of the Earth's ecosystems, thinking about it at the biological, social, and economic level. And then because I'm, at heart and professionally a machine learning researcher, I tend to think of this as a pipeline with lots of feedback loops, as you can see, that starts with data collection, then thinks about fitting models to data, and finally designing and deploying policies for controlling or managing a system. And we've already seen examples of a lot of these this morning. But I'll talk about sensor placement. Where do we take our observations? And there was a little bit of a discussion of that with the citizen science talk this morning. Where people have an opportunity to go, say, do surveillance for invasive species. Where should they go? Then there's the data interpretation process, which is to take that raw data, whatever it is, and for instance, apply computer vision to extract species IDs or individual identifications. Then there's the data integration process, and the talk this morning, I'm blanking on the name of the person from Caltech who was talking about integrating all of these different data sources, remote sense data, citizen science data, camera trap data, all these different things. Huge challenges there. Then there's model fitting, my favorite topic, of course, as a machine learning person, but then policy optimization. If we fit a model to the dynamics and distribution of a species, for example, then how do we optimize against that model? And actually, Yoshua Bengio kind of mentioned this problem when he was talking about how regulations and incentives, particularly regulations, create a large sort of convex hull that has a lot of corners, and corporations and intelligent systems in general, optimizers in general, will try to seek out those corners because those are the places that they can best exploit. So a big problem when you fit a model to data and then optimize a policy against it is the policy optimization finds the weakest aspects of your fitted model. And then finally, policy execution, of course. We'd really like to put our policies into play. Okay, so for this talk, I'm not going to try to hit all 6 of these, but I'll just talk about 4 of them and draw on examples from the work that I've been involved in one way or another. So we'll look at sensor placement, at model fitting, data interpretation, and policy optimization. So the first 2 things that I want to talk about are related to the TAHMO project. So TAHMO is an acronym for the Trans-Africa Hydro-Meteorological Observatory. It's also the name of a nonprofit corporation that's domiciled in the Netherlands, but whose goal is to have a sustainable business model for deploying and operating a very large network of automated weather stations in all of sub-Saharan Africa. The project had its origins in the work of 2 hydrologists, John Selker, who's here at Oregon State, and Nick van de Giesen, who's at the Technical University at Delft in the Netherlands. And they noticed that they saw this map here, which shows weather stations that are reporting reliable information to the World Meteorological Organization, which is one of the UN specialized agencies. And they noticed that there are huge holes in South America and in Africa. And what is weather data from weather stations is estimated to be worth something like $20 billion to the US economy every year because it supports things like crop insurance, which allows farmers to take greater risks in planting their crops and increase average productivity, agricultural yield, management of floods, transportation and other kinds of logistics. The benefits go on and on. Of course, air flight, air travel, all these kinds of things. So without ground data, it turns out, weather forecasts and so on are difficult to make with great accuracy in South America and Africa, compounded by the fact that they straddle the equator, and equatorial weather is very complex, much more so than temperate zone weather. So this is what our weather station looks like. It's a single unit created by a company called Meter, which is, I believe, in Canada. And this is the data logger. So there are these 2 boxes on a pole, basically. And the goal of TAHMO is to leapfrog Africa from being basically the worst sensed to being the best sensed continent in terms of ground weather observations. The current status is that we have about 600 stations deployed in about 20 countries in sub-Saharan Africa. We're particularly strong in the ones that are here in blue, so Ghana, Kenya, Uganda, Nigeria, and Mali. You'll notice despite areas that are experiencing substantial civil disruption in some cases, we're still able to operate weather stations there. So the first challenge that comes up in my, my pipeline is, well, where do you put your stations? And so this is a picture of Amelia Snyder and some of her collaborators during her visit to Benin, where she went to discuss how to, where to place we had a budget to place 20 new weather stations in Benin. Where should we put them? And of course, the main idea is that you want to place the weather stations so that when you use them to interpolate a map of the whole country, that you get an accurate map. So you want to reconstruct, say, a map of the temperature over the whole country, or precipitation, or atmospheric pressure, wind speed and direction, and so on. So in fact, our stations measure 7 different weather variables, and they have very different properties and scales. And so the first question came up was, well, how should we combine all of these different sensor readings to decide on an overall metric? We could treat it, for instance, as a multi-objective function, and then the question is, well, maybe finding the Pareto frontier and then choosing an operating point on that frontier. Or we could try to take a weighted sum of the errors for reconstructing each of these variables. What we decided to do was to focus on soil water that's available for agriculture, because the main consumer of weather information in Benin is rain-fed agriculture. And so something to look at there is something called evapotranspiration, which is the water that's used by plants and or is evaporated from the soil surface. There's a well-known formula called the Penman-Monteith formula that estimates or computes the potential evapotranspiration, which as a nonlinear combination of temperature, solar radiation, wind speed, relative humidity, and atmospheric pressure. And that's the potential evapotranspiration, because it depends on what plants are actually growing at that location. It assumes adequate precipitation, but we didn't want to make that assumption. So we added a kind of what we call a bucket model for the soil water content. And so on a daily basis, what it does is we have a certain amount of water in our bucket, and then some amount of rain falls, and that maybe fills up our bucket, or maybe even overflows to create surface runoff, but it fills the bucket. Then we calculate the water stress based on how much water is available here, and then use that to calculate to estimate the actual evapotranspiration that we expect. So we have the calculated potential evapotranspiration combined with water stress to get actual ET. And then we assume that amount of ET happens, so we subtract that water from the bucket, and that's the starting bucket level for the next day. And so from this, at each grid cell, and we have something like 1,200 grid cells just in the country of Benin, we can estimate the actual ET in each cell each day. And then we want to locate our stations to minimize the squared error in this estimated actual evapotranspiration. So how should we do that optimization? Well, as I say, we have, does it say it on here? It doesn't, but something like 1,300 sites. And we could imagine putting a weather station in each one of those grid cells. But of course, those are not all equally important for agriculture, and they're also not equally accessible in terms of being able to visit them to perform maintenance. So what the methodology we wanted to follow was to put together a list of candidate sites and then solve an optimization problem to choose a subset of them. And so what she did in her work was choose 60 candidate sites in 2 possible ways. One was to choose a set of well-spaced sites that cover the country just based on their distances. And the other was to choose 40 sites on top of 20 that were recommended by the domain experts from the local meteorological agency. And then, as I said, our objective function is the squared error between the interpolated evapotranspiration that's computed from the 20 chosen sites, whatever they are, and the true ET over the 1,374 grid cells. Now, of course, there's always a chicken and egg problem when you're doing sensor placement, because you need to estimate ET and so on. And for that, you need weather data, but you don't have weather data because you don't have stations. So there is a site called AWARE that tries to do its best to come up with estimates for these quantities by combining whatever ground stations are available, and there were something like 5 stations already operating in Benin at this time, satellite data, radar data, theoretical models, and so on. And so based on that, we use that, and I don't think that data would be really good enough to use for agricultural decision making, but maybe it's sufficient for sensor placement. We suspect that qualitatively it's probably getting things about right. Another challenge was that to evaluate a candidate set of stations, you then need to interpolate the daily ET over all 365 days of the year and then add up the squared error. That was very expensive to do a single evaluation. So instead we did a K-medoids clustering and then over the 365 days and chose 50 days that gave us good representation of the whole year. And then actually most of the work that was involved in this project was really involved in kind of validating this objective function. So that's actually our first lesson learned, that the hard problem wasn't really the computational one. The hard problem was, is this ET measure the right thing to be optimizing? And so in particular, we wanted to know, well, where does ET kind of focus the attention of the optimizer? So, and what does it focus on? So in areas that are very wet, it not surprisingly just looks at ET because there's plenty of water there. And so potential evapotranspiration becomes actual evapotranspiration. But the second thing that it really focuses on is regions of transition between areas that are going from wet to dry or dry to wet. I mean, sort of that boundary, because it really wants to put stations there. That's where it's making the most errors. If there are regions that are dry all the time, it doesn't need, it can put stations there because they're not changing too much. Wet all the time, same thing. It's in the area where there's transitions during the year that need the most attention. Okay, well, the results were that if we just used the recommended 20 sites from the experts, we had actually a ET interpolation error of 0.64. If we used our optimization over our 60 sites, that we got a lower thing. And if we actually combined 40 sites that were chosen for spatial coverage with 20 based on expert recommendations, then we got the lowest error overall. So I guess the first thing is the optimization. This maximal spacing is a solution if you don't do any optimization at all. Optimization improves the mean squared error by about 10%, and using the expert suggestions improves things a little bit more. And so you can see we ended up using 8 of the experts' recommended sites in the final solution. So the overall lessons learned, you mentioned, first of all, yes, most of the time was consumed with designing and validating the optimization objective. The objective was expensive to calculate, and so we had to do some simplifications there. Including expert recommendations helped, and much work is needed to incorporate secondary objectives. So as I'm going to discuss in the next topic, one of the things we would like is that every station would have 2 stations near it to support detection of sensor errors, to be able to sort of do majority voting among those stations. And that objective wasn't incorporated here. And the folks in the room thinking about submodularity will think that actually the original objective is close to being submodular. But when you add this kind of a constraint in there, you lose that property. You might be able to regain it by treating triples of stations as like a single macro station, and then probably we can get some submodularity. But we really wanted to find the optimal design. A factor of whatever it is, 1 minus 1 over e we'd really like to find optimal solutions. Okay, well, let's look at the second question, which is an example of data interpretation, I call it, or data cleaning in this case. And this is work by Ethan Derajinsky, who did a PhD with me back in, graduated in 2007, kind of laid the groundwork for more recent work by Tadessa Zamichael, who just graduated this year and is now at NVIDIA. So it turns out sensors break in unpredictable ways. Our data logger got attacked by ants who decided it would be a good place to build a house, and by wasps. This is wiping out these are the wind speed transponders, and This obviously was interfering with airflow between them. And so the strategy we're trying to use is to apply anomaly detection techniques to detect unusual sensor readings and then flag them. So we have these generation 3 state weather stations, and they report their data over a cellular data network to our sort of input database. And then our sensor diagnosis system, that's what sensor DX stands for, then copies that data to what's called the control database, and then flags data points that it thinks are suspicious for some reason. Customers can then access this control data and get only the points that are not flagged with a warning of some kind. The network manager, on the other hand, looks at those flagged data and decides whether to open a trouble ticket and assign it to a field technician to go visit that station and maybe replace it, clean the sensors, test them, recalibrate them, so on. And all of this stuff is done as with a set of microservices in the IBM cloud. And actually, our rain precipitation quality control has been deployed and is now in operation. So how do people do data quality control? Well, the traditional approach is really sort of like 1980s style AI. It's a rule-based system that raises an alarm if a rule is violated. So you might have a step test that says, for instance, if the temperature increased by more than 10 degrees in a 5-minute period, then you should raise an alarm. Or if it rained more than, half a meter in a day, that raise an alarm. There are usually flatline tests that say that, we would expect the temperature to vary somewhat. So if it's completely flat for a whole day or for some period of time, then maybe we should raise an alarm because it's a stuck sensor. That can happen if, for instance, the thermometer is underneath snow, and so it's just reading 0 degrees Celsius. And then buddy tests that compare, say, 2 identical sensors or sensors at 2 stations that are near to each other. But the modern approach that we would like to advocate is probabilistic quality control. Maybe we would call this AI circa 1990 instead, which is to define, and so we define a state variable for each sensor that says it's either 0, which means okay, or it's 1, which means it's broken. So this may be a little bit like our TB patients this morning. And then we have to estimate these 2 probability distributions. What is the probability of seeing a particular observed value when the sensor is working? And what's the probability of seeing that when the sensor is broken? And then, and we have some prior beliefs about the sensor state. And then we can apply probabilistic inference to calculate the probability of the state conditioned on the observations. And so visually, you might have something like this. Maybe if the sensor is working, you expect this probability distribution. And so if you observe a value of 3, well, its probability is pretty high. Whereas if it's broken, you might expect something like the uniform distribution over some big range. And so if we observe a 3, we're happy, but if we observe a temperature of 5, maybe it's broken. Now, obviously, the temperature is changing, and so the signals are non-stationary, and that poses big challenges for us. We'll come back to that in a moment. But one of the big advantages of probabilistic quality control is that you can exploit the joint distribution among multiple sensor variables, right? So for example, if we consider temperature and relative humidity, they are strongly negatively correlated. As the temperature rises, the relative humidity will generally drop unless you're inputting additional moisture into the system, say by advection, wind off the Gulf of Mexico or something would be adding moisture. So, so suppose you observe this temperature, this temperature humidity combination, this red dot. Well, if you looked at that just as, is that a typical air temperature, it would say, yes, it's okay, it's a warm day, but it's well within the observed range. And similarly, is a relative humidity of 78 or whatever, is that a reasonable relative humidity? Absolutely. And yet the combination is highly unusual, right? Way off of the joint distribution. So that's the big advantage of probabilistic modeling. But the disadvantage is that when we raise an alarm and say this red point is weird, we don't know which sensor is at fault. Is it the thermometer or is it the relative humidity sensor? So we really need to have other evidence that might exonerate the thermometer, Like, for instance, we might look at the short-term temperature trend and it looks perfectly reasonable versus evidence that might influence the relative humidity, like information from a neighboring station, because relative humidity is quite smooth in space. So we need some sort of joint diagnostic reasoning. And so we're going to be doing joint probabilistic inference. And I realize my notation is really horrible here. In general, the idea, let's just look at this formula here, is we have a collection of observed values V and a collection of state variables S, and we want to find the map state of the system. So what is the state assignment to the variables S that maximizes the probability, the likelihood of the observed observations? And so that's kind of the reasoning. And so a Bayesian network for this might have a state temperature for state variable for temperature, a state variable for the relative humidity sensor, and then this joint distribution between the two of them. So now there are three challenges that we run into. First of all, it's really hard to build these models that say, well, given that the sensor is working correctly, what should the temperature sensor be right now? It really needs to be some sort of a Markov model or a time series model because of the non-stationarity. The second thing is that as the number of variables grows, the number of possible values of the configuration of the system grows exponentially, right? We have basically 2 to the power of the number of sensors. And the computation is overall times t as well. So it's 2 to the power of the number of sensors times the number of time steps. So very rapidly, this becomes infeasible computation to do exactly. So Ethan came up with a couple of solutions. The first one, actually, he didn't come up with. That's from Tedessa. So I meant to edit this slide, but is the idea of what we call the View-Anomaly-Diagnosis Framework. And the other two, search, map, and filter and commit, are from Ethan. So let me briefly describe those. Okay, so the View-Anomaly-Diagnosis Framework is basically, we're going to kind of divide up the big problem of understanding all of the variables at all time periods into a collection of views, kind of in the database sense. So we might define one view, which is the joint view of temperature and relative humidity at a single time step. And another view might be the temperature for the last 3 time steps as a short little time series. And then we're going to train an anomaly detector for each view. And the main advantage of training an anomaly detector is that it outputs an anomaly score on a sort of standardized scale, so that we're not trying to predict the actual temperature at each time step or the actual relative humidity, but just how unusual it is relative to some baseline training data. And so then we are going to fit probabilistic models to these anomaly scores instead. So we treat the anomaly scores as a kind of derived observation. And so we might say, well, what's the probability of observing this anomaly score given that the temperature and the relative humidity are both working? And so the anomaly score should be very low in that case, right? If it's high, then one of these parent sensors is broken. Unfortunately, to estimate these probability distributions when one or more of the sensors is broken, we don't have very much training data. So we have to simulate injecting faults to fix those, to fit those cases. So the advantage of this approach is it gives us a lot of modeling freedom. We can define views and anomaly scoring methods very freely over lots of different combinations of sensors, using different kinds of anomaly scoring techniques and so on. The disadvantage is that in some sense, multiple views that involve the same variable could end up double counting evidence, right? And so, for instance, this temperature time t is in both of these two views here. And that's actually important because it helps us exonerate the thermometer. If this anomaly score is low, then the thermometer is probably not broken. But we're using that temperature reading in calculating both of these anomaly scores. So they're not independent. There's correlation there. We don't know whether that's really a problem or not, but it's a great engineering solution. Okay, well, so Tedessa designed 4 different kinds of views. They involve sometimes a single variable at a single station, sometimes multiple weather stations, sometimes multiple variables, and so on. Okay, so the second idea is how do we avoid the exponential cost of doing the map inference finding the most likely configuration of the state variables. Well, we use a greedy algorithm. So we start with a state in which all the sensors are working properly, and we score its likelihood. And then we consider breaking one of the three. In this case, let's say there are three different sensors. Breaking just one of the sensors at a time and scoring each of those configurations. And then this is the one that has the highest likelihood. So then we expand it and we consider breaking one of the two remaining sensors and so on. And we end up with this being the map configuration. So this is basically a greedy algorithm for finding the map configuration. And it's not guaranteed to be optimal, of course. But Ethan did a bunch of experiments in his thesis and showed that this worked better than a lot of other state-of-the-art probabilistic inference methods, like expectation propagation, for example, and some variational techniques. The last idea is filter and commit. So you know, in some sense, as a probabilistic inference problem, you would like to collect up all the evidence you have. Let's say, you know, from when the weather network was first installed until the death of the universe. And then you just have this big probabilistic inference problem to figure out when sensors were broken. But of course, that's not useful. You need something that is more online. And so then how do you handle that? Well, we have this idea of basically of filtering. So right at each, like in a Kalman filter, at each point you can be estimating the current state in some sense, but we're not going to do the full bidirectional reasoning, which goes back and uses current observations to revise our beliefs about the past. As we're filtering, we're going to commit to our beliefs, our map solutions at particular time steps. So in this Bayesian network here, the observables are these anomaly scores. So this is, say, readings from our thermometer, a little local time series. This is our relative humidity readings, again, a little local time series from time 0 up to time 2. And this is then that joint view of temperature and relative humidity. And so we would say that this is observation time 2. So we have all of the observations up to time 2 allow us to score the 5 gray nodes and get those anomaly scores. And then what we're going to do is do map inference over these 6 colored nodes here, these 6 state variables, and find the map assignment to these, and then we're going to commit to the 2 red nodes. And so we include these other nodes because we're doing the joint probabilistic inference, but these have only partial evidence, right? We don't yet have the observations at time 3, which are also important to determining the state of the sensor at time 1. So we will do this inference problem, then commit to the red points, and so they become observed. We treat them now as observed, and now we advance the clock. Now we add the data from time 3. That lets us evaluate 3 more anomaly scores. We then do joint inference on these 6 colored variables, and then we commit to the red variables, and so on. And so this is how we manage this. Is we never go back and reevaluate things. It's a slight lie, because we can have a problem where a sensor reading was stuck. We can sometimes have a case where the cellular connection for a weather station fails. So the data logger is still collecting data, but the cell signal dropped off for some reason. And then maybe 1 or 2 days later, it's able to make the cellular connection, and suddenly we get data for 3 days uploaded from that station. In that case, we actually have to rewind this inference back to that point and redo it. I went too far. And bring it forward again, and we do that calculation. Okay, well, we wanted to compare this kind of joint inference probabilistic approach to something that is more like the traditional rule-based approach. We didn't implement the rule-based approach, but instead we just said, well, suppose we only used single sensor time series views, because that's very much what those rules can do, is they look at short-term changes in a single sensor reading. And so we compare them. We did this for a set of 4 stations from a weather network in Oklahoma. Oklahoma has the best weather networks in the world, and so they have beautiful data. So we compared the accuracy of the single sensor view at a fixed level of recall, and compared our precision. So, so the idea by recall, we mean correctly detecting broken sensors. And then we're trying to maximize our precision or minimize our false alarms. And so the blue lines are the baseline system that only looks at the individual sensors by themselves, and the orange is the joint probabilistic system. And so we can see that we're basically doubling the precision of our model while maintaining to achieve the same level of detection of faults. I guess, but of course, the converse is that doubling the precision means that we're reducing the false alarm rate from something like 85% down to 70%. So one of the painful facts of life with anomaly detection is you just get a lot of false alarms, and that's why we have a human network manager in the loop to decide what's going on. Okay, so the lessons learned here was the first one is that we originally hoped that all the anomaly scores could be computed using general purpose anomaly detection algorithms like the isolation forest. And this kind of worked okay for some variables if we block the year out into just 20-day blocks and pretended that the data was stationary within those blocks. But it really doesn't work for other variables, like rainfall is a nightmare. So we've ended up having to bite the bullet and do detailed probabilistic models for things like precipitation and wind speed. And we're basing that on comparing neighboring stations. So that's our next step, is using neighboring stations to diagnose each other. And this exploits the fact that even though the weather signal is very non-stationary, nearby neighbors are experiencing the same non-stationarity. And so if you subtract them from each other, you're getting a stationary signal. And the other drawback of the approach is that it really required us to have simulated faults, which are not simulating things like wasp attacks or ant infestations, right? They're really only simulating certain faults that we can anticipate. And so we'd really like to explore a different model where we do what's called consistency-based diagnosis. And in that approach, you basically look at if the joint distribution of a bunch of sensors has low probability, you ask, well, what sensor, if I deleted it from the model, would make the rest of the stations have higher probability? And you just keep deleting sensors, thereby labeling them as faulty, until the rest of the data looks reasonable. And the advantage of that is you don't have to have fault models. Okay, well, the last two topics I want to talk about are ones involving model fitting, and I'm going to need to, let's see if I've timed this right. The model fitting work was really the key mover behind all of this is Dan Sheldon, who's a brilliant young scientist and was an amazing postdoc to work with. And the challenge here comes from the eBird project. So many of you know that eBird is a citizen science project in which volunteer bird watchers fill out checklists nowadays on their smartphones of what bird species they saw and sometimes how many individuals they saw on a given day when they went out bird watching. And that data is then processed at the eBird website using some spatiotemporal tree models, which are supervised learning models that have been developed by Daniel Fink. And he's able to then provide species distribution maps for every day of the year by interpolating and using the predictions of these models. And looking at these maps, Dan wanted to say, well, shouldn't we be able to build something that's more like a causal or explanatory model? Can't we fit a model of the dynamics that would explain that, when we see the thing go from April 17th to 25th to May 2nd to May 9th, it sure looks like birds are flying from south to north as they're migrating northbound. We know that that's true. Can we fit models that would do that? And so how could we do that? Well, imagine for a moment that every one of these little birds was carrying a cell phone. And so we had a GPS track for each of the individual birds. then bird one might start in, and suppose we lay down a grid of cells over the United States, then bird one might have started in cell A, then flew to F, then to L, then to R, then to W. And it would be really easy for us to fit a probability transition model, right? We want to know if birds are in cell A, what's the probability that they'll fly to cell F or G or B or L or whatever, right? Every night of the year as a function of things like wind speed and direction, humidity, temperature, things like that. And so that's the model we'd like. And if we had this kind of data, we'd be golden. I mean, if you write down the likelihood function, it turns out the sufficient statistics you need are, you need how many birds were in each cell on the first night of the period, and then you need for each pair of cells I and J, how many birds flew from cell I to cell J on the day from going from time t to time t+1. Bird migration mostly happens at night, so that would be in the night from day t to day t+1. And if you have those statistics for the birds in a given species, then this is the likelihood model, and you can do maximum likelihood inference. But we don't have that. Unfortunately, all we have is aggregate counts. So that's fine for this first one. We get the aggregate counts the first night, but we don't have these transitions. We only have the marginal count of the number of birds in that cell at that time. And actually, I'm telling a little bit of a fib here because we don't have the actual counts. We have extremely noisy observations that are presumably we're only detecting a very small fraction of the number of birds that are in one of those big cells because we just have ground observers. But hopefully it's proportional in some steady way to the number of birds in those cells. Well, the question that Dan raised in his work was, can we still fit this model? Because you can still imagine that if you had a proposed value for theta, the parameters in the model, then you could, in some sense, simulate a bunch of bird migrations according to theta, calculate these marginal statistics, and then compare them to the observations, and back propagate that back to improve your estimate of theta. So it's kind of possible in principle, and you can actually investigate whether the model is identifiable because it's a latent variable model, and it is identifiable under a broad range of conditions. And so Dan invented this thing called the collective graphical model because we don't want to actually have to do those, simulating huge numbers of individual bird trajectories. That would be a very expensive Monte Carlo approach. Instead, it turns out that you can analytically marginalize away those individuals and just get a likelihood function over the counts themselves. And so he called that the collective graphical model, and he worked out all the mathematics for it. And you end up with something that looks like this, where your observations are these counts, and the sufficient, and then the latent variables are the sufficient statistics. And the beauty is that they still have this same tree structured factorization, so it's still a hidden Markov model in some sense. Okay, so to evaluate it, of course, it turns out computationally it's still a real mess, very expensive, and we can prove various hardness results about it. So we developed a little test bed for a synthetic migration benchmark, and then we evaluated various algorithms. So Dan and I had a paper at NeurIPS in 2011 that used Gibbs sampler on something called the Markov bases, and on a very small network with only 16 grid cells, we could get the error down in 250 seconds maybe for that very simple model. But if we scale that up to 49 grid cells, ooh, it's starting to take a long time. And so then over the years, we've come up with various improvements so that we've really been able to greatly reduce the computational cost with some approximation error issues for this proximal algorithm. And various other collaborators have gotten involved at various points along the way. But the result is that we have been able to fit some bird migration models. So here's one model, and you can see that it sort of captures the northbound migration. Southbound is pretty chaotic. So it's not a super good fit. We watch the southbound again. There's a lot of funny business happening. But what are the lessons learned from this? It turned out that we really couldn't use this fitted model to do bird migration forecasts. it was too unstable, and it also tended to do weird things. I mean, because it's a causal model, it enforces, in some sense, conservation of bird mass, right? That in order for a bird to show up at some site, it has to have come from someplace else, or have to have already been at that site. And but this causes the model to do weird things. So it sometimes stores unobserved birds, stores birds in places where we have no observers, like off the coast of North America or up in northern Canada, where there just aren't very many eBirders. And then when it needs them to explain bird sightings in the middle of summer, it just pulls them in. So you have this southbound migration from Canada to explain how the birds showed up in New York State. And it was very hard to constrain the model. I mean, the one I showed you was a very cherry-picked case where it was pretty good. But we had a lot of trouble constraining the model to prevent trivial or ad hoc solutions and to impose some sort of coherence on the migration. And so the birdcast people at the Cornell Lab of Ornithology basically are using the sort of snapshot models that Daniel Fink is fitting, combined with radar data. So the painful lesson here was that although these global causal models are very elegant, they're very difficult to control, and turned out not to be very practical. Okay, well, the last topic I want to talk about is invasive species management, and I have to do this in just like 5 minutes. So the final project was work by 2 students, Majid Alki-Taligan and Kim Meyer-Hall. Kim was in applied economics and was a student with Joe Alber's faculty collaborator. And we were studying tamarisk, which is an invasive tree that invades in river networks. And it's invaded more than 3 million acres in the western United States. It outcompetes native vegetation and humans for water, particularly in New Mexico. It's been a big problem in the Rio Grande Valley. And of course, it has negative impacts on plant and animal biodiversity. So the question is, what's the best way to manage this? And this morning we saw several other talks about management problems. And so coming up with optimal policies for management is maybe the core goal in computational sustainability, I think, a lot of the things we're seeing. So in our case, we formulated this as a Markov decision process. Our collaborators were interested in studying kind of stylized problems to understand the shape of optimal management policies, not to build a deployable model that sort of engage with all the real world complexity. So in our stylized model, we imagine a river is just a tree, a binary tree, with a set of edges, and each edge has some number of sites, in this case 3, where a plant can live. And the site can either be empty or have a native plant in it or have a tamarisk tree in it. And then at each time step, those trees, some trees die a natural death, and then the surviving trees make seeds, and then those seeds propagate through the river network. And some of the seeds can travel arbitrarily long distances downstream. There's even a small probability of upstream travel, maybe assisted by a bird, for example. And then they arrive at these sites, and then they compete stochastically for which one gets to occupy and establish itself at this site. So in this case, these 4 seeds had 2 tamarisks and 2 natives. The tamarisk won, quote unquote, this. Now we can write this down as a dynamic Bayesian network, but unfortunately, because of this kind of global propagation of seeds and the competition to each site, everything gets coupled to everything else, and you don't get any really helpful factorization. So it's a very loopy network, and it's easy to simulate from, though. So we basically used a Monte Carlo sampling to estimate the transition probabilities. So to solve our MDPs, I should say what our objective is. So we assign a cost to each to being invaded, and then a cost to the various interventions that one can do. So what are the treatments that one can do? I guess I skipped over that. But one thing you can do is you can go to a site and try to kill this tamarisk tree, the tamarisk trees on this edge here. You can also go to an empty site and try to plant native trees in these empty sites on this edge. So the actions are on edges, and they affect all of the cells in that edge. Or you can do both. You can kill the trees and try to replace them with natives. or you can do nothing. And unfortunately, natural resource management generally has very low budgets. And so we looked at cases where you could only afford to treat maybe one or two edges. Killing the natives, the most expensive thing is to kill and try to replace kill the tamarisk and try to replace. Cheapest thing I think was just to plant new trees. But in any case, we want to minimize the expected discounted costs subject to an annual budget constraint. So it's a fixed horizon MDP problem. We were looking at a 100-year horizon or something like that. The computational approach was basically for to enumerate a big transition table. So we're keeping these problems small enough that we can actually enumerate the MDP as a table, and then do enough Monte Carlo sampling to estimate each of the transition probabilities to high accuracy. Then apply value iteration and get the optimal policy. And obviously this doesn't scale to large problems, but it was sufficient for our needs here. But to do a real problem, you'd have to start doing value function approximation or policy search or something like this. Okay, so the first lesson learned was that actually computing the optimal policy was not the hard part. It was understanding the optimal policy after we computed it. In applied economics, you really can't just publish a giant table and say, see here, this is the optimal policy. You need to do policy analysis and understand, well, what does it look like? So Majid came up with this kind of a visualization for a river network, where the gray edges have nothing living, no trees in them. The green have natives, and the red have the invader. And in this case, there's just one slot per edge. And then the optimal actions were, the optimal action was try to eradicate the invader, and this would be plant a tree. And you could have both a circle and a square on an edge, meaning, eradicate and plant. And then we printed out these for this table. So there are, after you take into account symmetries and so on, you don't have 40,000 of these, but you still have a few thousand of them. And then Kim Hall basically spent months studying these, cutting them up and clustering them physically to try to extract general rules. And an example of the kind of general rules she would come up with is that the optimal policy for an edge depends on the state of other edges. So in this case, the optimal policy for the optimal action is to eradicate at this edge and then plant something in this region here. And the optimal policy in this case is to eradicate and then plant a native species in the same slot.
And just a 5-minute warning.
Okay, great. And then, well, why? This requires reasoning about the dynamics of the system. So Kim argues that in the second case here, these native species are kind of providing a sort of barrier. It's not a real barrier because a seed from this red part here could travel all the way down here. There's nothing, the trees are on the river bank. They're not in the river. They're not preventing seed flow. But the probability of that is low, or compared to the probability of just traveling one step, and the bad seeds can't establish themselves here. So it's a kind of like a barrier. Anyway, so the lessons learned in this thing were there's a huge need to be able to extract abstract behavioral descriptions of learned policies. I mean, Kim is bringing into here vocabulary like upstream and downstream, which is relational, whereas our MDP was just as a flat table, right? Notions like barriers, process descriptions like start eradicating at the top and go downstream to the bottom. She's bringing this vocabulary, and how could we acquire that vocabulary and then map the learned policy into it? Another problem was that I think she was really, we just printed out the so-called optimal policy, but we know that there could be many ties in such an optimal policy. And she might have been able to get simpler descriptions if we had shown, tied actions, which we failed to do. And you could go even further. Maybe the Q values aren't identical, but one action is only slightly worse than another. And so maybe you could get an even simpler policy if you're willing to introduce some approximation. So, and then another lesson was there's really a need to handle multiple objectives. as it was mentioned earlier today, it's basically impossible to put a price on something like species extinction. And so you could put that in as a secondary objective. We think that that we should adopt a constrained MDP approach. So put a chance constraint on this, and find the optimal policy subject to a constraint that the probability of species extinction is less than, say, 1 in 1,000 over 10 years. So my overall summary for the talk is some of the lessons we learned were it's really important to engage local experts and incorporate their knowledge. It's super important to spend time formulating and validating your objective function, which was clear in the evapotranspiration case, but also in the species extinction case. Real data is non-stationary, and this was really a big challenge with trying to use kind of IID techniques for the weather station problem. I was hoping to avoid a detailed modeling of all the non-stationarities, but I think that's just, sometimes you just have to bite the modeling bullets. And finally, explainable AI, explaining the model predictions and the outcome policies is a huge challenge. And so with that, I'll thank all of these people. The other people that worked on the collective graphical models work was Liping Liu and a host of grad students at UMass, Kevin Winter, Garrett Bernstein, Tao Sun, Xiaojin Wu, and Akshat Kumar. Thanks to Steve Kelling at the Lab of O and Daniel Fink, and to the National Science Foundation for a long series of grants. Okay, I will stop there and answer questions.
Awesome. That was a really awesome talk. Thank you, Professor Dietrich. We do have one question in the chat so far by Genevieve. And
Okay.
Genevieve is asking, have you visualized how the difference between the uniform spacing, expert placement, and your optimization results scale with the number of sensors placed? For example, does the optimization make the biggest difference when you're placing many sensors, few sensors in intermediate regimens?
I don't know the answer to that question. It's a good question. I mean, you know, just in the limit of lots and lots of sensors, it really wouldn't matter, right? So probably it makes the most difference when you can't afford to put very many sensors out and you have to think hard about it. Yeah, great question.
Yeah, I think something, I mean, I've done a little bit of work in this space of informative sensor placement, and we've observed kind of empirically many times this interesting phenomena where when you're placing very few sensors, kind of all sensors are equally good. You know, you have no information at all and every sensor is adding a lot. When you're placing many sensors, yeah, you're kind of densely covering the space. And again, it doesn't really matter whether you've used an optimized policy, but then kind of in these intermediate regimes, you can see big differences between yeah, policy place sensors and just more uniform spacing. I think it's, yeah.
Yeah,
I actually have a follow-up.
I was hoping to include more kind of challenges for the future in my talk, but I guess I'm still suffering the pain of the lessons learned.
I guess I have another kind of high-level question is, you know, all the decision-making stuff that I think is really interesting relies on these models of, you know, bird migration or plant distribution. I mean, how good do you think how good are the models that we have? How good are these estimates based on the data sets that we use, just kind of qualitatively?
Yeah, I mean, the models are not very good, of course, I would say, right? In my experience. But then another question is, well, how good do they really have to be? I mean, often qualitatively, you can, I think you can get a sense of what the good policies are without having super accurate models, because you need to be improving over current practice, and current practice is often extremely heuristic. So so maybe we don't need super good models. You know, I'd say a real, to use another use of the word model, a real role model for me is Yadin Shades, who's at CSIRO in Brisbane in Australia. She's looked at a lot of problems that involve partially observable MDPs, where or what are called mixed observable MDPs, where you can only observe some of the state variables. And we're actually going to hear from Jonathan Ferrer, I think, who's a postdoc of hers that I'm sort of peripherally advising. And she often does a lot of engineering of the state space to make it small enough to be solvable with, say, pointwise value iteration techniques. And there's a lot of taste and knowledge brought to bear there. And then if there's some uncertainty about what the model is, the real model is, she can set up a hidden variable that is a switch among the dynamics of, say, half a dozen different possible dynamical models, and then the system can reason about which model is maybe the right one to use, right? So it maintains belief state over the models, and it's kind of doing the full Bayesian thing you'd like it to do in some sense. So so I think that's a very practical methodology where you can build in your expert knowledge, but then the uncertainty that really matters, you can incorporate that too.
Thank you.
Awesome. So with the interest of time, I think we'll end questions there, but be sure to reach out to Professor Dieterich. We're going to take a quick break, so please come back to Zoom, the webinar, by 3:40 p.m. Eastern Time, and then we will get started with the presentation group 3.
Okay, thank you very much, everybody.
Thank you. Are we ready, Hari? You're muted.
Hi everyone, let's get started with presentation group 3. And we have a lot of really exciting talks in this group. And the rules are the same. You know how much time you are allotted and try to complete your talk within that time. And we'll try to allot around 1 minute of questions based on how many questions you get for your talk. And for this group, we'll let you share the screen. So I have updated the settings. So you can just share the screen, and whenever you are done with the question answer page of the talk, feel free to just stop screen sharing so that the next person can share their screen. So I'll invite Brian Wilder from Harvard University, who will give a talk on Bayesian inference for infectious disease outbreaks. Brian.
Okay, thanks, Hari. My name is Ryan Wilder. I'm a PhD student at Harvard, and this talk is going to be about Bayesian inference for infectious diseases. So as you might imagine, the most approximate motivation for this work is the COVID-19 pandemic, which, again, as I'm sure we're kind of all familiar with, is characterized by a lot of unknowns, as are many sort of emerging infectious disease outbreaks. So we just really don't know from observing the kind of aggregate noisy data we have exactly what the dynamics of the outbreak are in a particular population, and whether there are new outbreaks starting in particular places. And so in this talk, I'm going to provide an overview of some recent work on two scales addressing these kinds of issues. And the focus in both pieces of work here is going to be on Bayesian methods that let us make inferences about the underlying unknowns in the dynamics of the outbreak from the kinds of aggregate information that we can actually observe. So the first part of the talk is going to focus on methods for population level inference, asking how the dynamics of the outbreak vary across different kind of populations around the world. And then the second is going to be at a finer grain scale about community level inference, asking how we can detect outbreaks at a local level from the kinds of sparse data that we'll have available from testing programs. With that, I'll go ahead and dive into the first part of the talk here about population level inference. So we know that there are a lot of population-specific demographic factors that strongly influence the dynamics of COVID-19 outbreaks in particular locations. Things like the distribution of agents in the population, comorbidities, household structures, all of these things play an important role in transmission and the effects of the disease, but existing models largely don't include this kind of population-specific demography. And so this work, we introduce an agent-based model with more detailed demographic modeling, along with Bayesian methods to recover unknown parameters in the model. And then we use the model as a tool to ask questions about the differential dynamics of outbreaks in different populations and the policy implications of those differences. So this work appeared recently in the Proceedings of the National Academy of Sciences, and it's the result of a collaboration with a number of others at Harvard and MIT. I'm going to start out by kind of briefly introducing the model. I mentioned earlier that this is an agent-based model, which means that we simulate people at an individual level, right? Millions of people that comprise a given population. And for each of these individual agents, we're going to keep track of a few attributes that are specifically relevant for characterizing both their behaviors related to transmission and the impacts of the disease if they contract it. And the first of these variables is age. The second is comorbidity status. In particular, we keep track of diabetes and hypertension. And finally, we also model household structure explicitly. So this is the set of other individuals that each person is together within a household and who they have particularly high rates of contact with. Each of these agents is then embedded in an overall SCIR type model. And this means that we're going to track their progression through different states measuring their exposure to the disease. Every individual starts out in the susceptible state, meaning that they haven't been exposed yet. And then they can have contact with other individuals through two sources. The first is a contact matrix that captures overall patterns of aggregate contact in the population. So this, for example, would have an entry saying the average number of daily contacts between someone who's 20 years old and someone who's 40 years old. So looking at these age stratified patterns of contact. And then the second source of contact is a model at a more granular level reflecting the household dynamics that I talked about earlier. Once agents come into contact with someone else who's infected, they're exposed, and then with some probability, they actually contract the disease and progress to potentially more and more severe disease states. So they start out before symptom onset, and then with a probability that depends on their age and comorbidity status, can progress to more severe forms of the disease, eventually potentially culminating in death. To a large extent, we can parameterize this model using estimates from the existing literature, but there are still a variety of unknowns that characterize the dynamics of the outbreak in a given population and that are not directly observable. The first of these is the probability of infection on exposure, which captures this aggregate level of transmissibility of the disease. The second is the start time of the epidemic, right, when the virus SARS-CoV-2 was introduced into a particular population. And finally, the fatality rate, since we know that there's also variation between populations potentially there. Inference is a little bit complicated for this domain because we know that case counts, right, the main sort of source of data that we have, significantly understate total infections, since many people just aren't tested and don't show up in kind of confirmed case statistics in the first place. And so to ameliorate that issue, we use the number of reported deaths to calibrate them. And we also, and then to sort of hedge against the potential for underreporting, we also include a sensitivity analysis to that possibility. But in any case, the goal is to be able to find a posterior distribution over those unknown population level parameters after conditioning on the observed series of deaths that we see in a given outbreak. And we're going to formalize this as doing inference in a Bayesian generative model. So here's the generative process that we're hypothesizing underlies the observed dynamics. The sampling process starts out by sampling values of these population level parameters from prior distributions. Then we'll run the model given those parameters, and the model is itself stochastic. And so that gives us a distribution over outcomes, and we'll sample a realized trajectory of the number of daily deaths in this place over time. And then roughly the idea is that we'd like to be able to compare that to the series of deaths that we actually saw, and then back out an inference about what happened further up the chain here, right? What the likely latent states of the model were, and what the likely values of the population level parameters are that underlie those observations. So to formalize the inference process more slightly, when we talk about conditioning on reported daily deaths to obtain this posterior distribution, we're going to be comparing two quantities. The first is the output of the model, which I'll denote D1 through DT, and this is the number of deaths on days 1 through day T in simulation. And then we'll have observations O1 through OT, which denote the number of deaths that were actually reported in that place in the real outbreak. Given those two quantities, we can define a likelihood function, which gives the probability of seeing that set of observations if the true series of deaths was actually D1 through DT. And we specify that observation model as a negative binomial distribution, where the negative binomial is essentially a generalization of the Poisson distribution for heavy-tailed count data. And that distribution takes two parameters. It's going to be centered on DT. So on average, we'll observe whatever number of deaths were seen in simulation, but then there's an additional variance parameter that captures sort of additional variance reporting. And given that likelihood function, I'm not going to go into a ton of detail here. Basically, we use a method called self-normalized importance sampling, where we draw a large number of samples from the generative model, and then essentially weight those samples according to the likelihood function to get samples that are then drawn from the posterior instead. Given that sort of inference methodology, the question that we really want to ask is, how can the model help us understand variation in the dynamics and the progression of the outbreak across locations? And here, I'm going to show results for two main estimates. The first is R0. So this is the average number of new infections that are caused by a single infected individual. And this gives us a measure of the kind of aggregate transmissibility of the disease in a given location. And then the second estimate that I'll show is the fraction of each population that was infected during the first wave of the outbreak. And I'm going to sort of compare these estimates for three locations that were especially hard hit in the first wave of the outbreak: Hubei, China, Lombardy, Italy, and New York City in the United States. Here's the first set of estimates for R0. So this plot is showing the posterior density, right, a histogram over the most likely values of R0 for each location. And we find evidence for pretty substantial variation across populations. For example, between a posterior mean of about 2.2 in Hubei to 3 in New York City. And this indicates that something about these kinds of different demographic and social structures is kind of producing differences in transmission. across these locations, which of course has implications for downstream control, right? It tells you that you'll need stronger interventions in New York City compared to Hubei, all other things equal. Looking at the second set of estimates for the fraction of people who've been infected, we estimate a substantial kind of extensive infections in all locations, ranging from about 7.5% of Hubei province in China to just over 25% of New York City infected in the first wave. But it's important to note from a policy perspective that all of these estimates still leave this kind of substantial potential for new outbreaks, because none of them are sufficient to guarantee, quote, herd immunity, right, where the fraction of people infected is sufficient to contain future transmission. And so in the paper, then, we explore further the kinds of policy implications of these estimates for controlling second waves, where there's this interplay between the sort of impacts of the first wave, as well as the different patterns of age structure contact in each population. And we find that there's really sort of a need for targeted policies that can leverage the particular circumstances and dynamics of the outbreaks in each of these places. But with that now, I'm going to move on to the second part of the talk about community level inference. And so before I was talking about inference at the level of states or large cities, millions of people, now I'm going to ask how we can quickly detect and mitigate new outbreaks at a very local scale. And this is joint work with Michael Mina in the Harvard School of Public Health and my advisor, Bill Tombe. And the motivation for this work is that one of the sort of most compelling options for being able to resume normal activity is to have testing programs at individual colleges or workplaces. And this is something that we're beginning to see pop up, where we'll regularly test at least some fraction of the population to get a sense of whether there's a new outbreak starting. And so that means that we're going to see data that looks like what's illustrated on this slide. There's some true number of infections per day that are occurring in the population. But then after whatever sampling process, we only get to see a portion of that, which generates this much sparser and noisier time series. And so clearly, if we look at the plot on the left, we know that this is an outbreak, right? There's exponentially increasing new cases over time. But after seeing just a small slice of the data, it's not immediately clear, especially in the early stages where intervention is really critical, whether a new outbreak is starting or not. And this is potentially a problem because existing methods are largely tuned to the case on the left-hand side. They largely assume that you're getting to see the full data, or at least you're in a large enough population that the sampling variation averages out. But when we want to generate actionable recommendations at local scales, we need to be able to work with the data on the right that's potentially really sparse, really understandable, really noisy. And we'll pose this again as a Bayesian inference problem, where we want to get from the observed data, which is the positive tests, to a measure of the rate at which the epidemic is growing in truth. And I'll formalize this as RT. This is something that a lot of us are probably much more familiar with than we were a few months ago. But roughly this gives the average number of new cases or new infections that a single person would cause at time t if they were infected. So this is a measure of transmissibility over time. And we want to be able to detect if this is spiking up. So again, we'll start by writing down a generative model for the observed data. So we'll model the ground truth value of RT, this time series, as sampled from a Gaussian process. And this, I think we have a tutorial about this later, but basically this is just a non-parametric sort of prior over smooth functions. And so we get some ground truth RT, and then the number of infections is generated by a disease model, which is roughly a branching process style model where the number of new infections is Poisson distributed based on the number of people who are currently infected, scaled by whatever RT is right now, right? Modulating transmissibility up or down. However, we don't observe infections directly. What we actually observe is mediated by some observation model, which subsamples the population to get whatever positive test results we actually see. And here, these observations can depend on whatever the biological properties of the test that we're using and when people typically test positive over the course of their infection, as well as sort of within host variation, viral dynamics. It can depend on the sampling method. If people are kind of opting in, right, just getting a test with some probability themselves, or if we're deliberately subsampling the population either cross-sectionally or longitudinally, all of these things influence the observed dynamics. And so now to do inference, we're going to propose a stochastic variational inference method that will try to recover a posterior distribution over RT from the observations. Now, the main challenge here is that there's a large number of latent variables in between the observed case counts that we see and the true value of R, right?
Brian, please complete in next 2 minutes.
2 minutes, cool. So there's daily infections that we don't see when each individual tests positive, the portion that we subsampled for testing. If you add this up, even in relatively small populations, you end up with tens or hundreds of thousands of discrete latent variables that are really analytically intractable to deal with. And so the solution that we propose, called GPRT, is a variational inference method. So we're going to approximate the true unknowable posterior or uncomputable posterior distribution via multivariate Gaussian. And we'll find the best approximation measured by the Cal divergence within that approximating form. And I'm not going to go into a ton of detail here. It's a paper. I'm happy to talk about it more if you're interested. But roughly, we're going to try to derive a modified variational objective that's more amenable to stochastic updates, because we don't have the ability to do anything analytically. All we can do is sample the model. And then given that objective, we propose lower variance estimators for gradients of essentially the likelihood function, which feeds into the variational objective, which let us substantially improve the computational efficiency of the algorithm. And given all of that, we sort of go back and forth between simulating the model to generate gradients with respect to our approximating parameters, and then updating those parameters. So I'm going to close out the talk here by showing an example of what this looks like. So here's a simulated example where we have a time series of cases on the left. Notice that the y-axis tops out at 8. So this is a pretty sort of low end situation. And previous methods just really kind of don't know what to do with this sort of data. They spike all over the place, get results that are not terribly sensible. But our method is able to much more closely recover the ground truth because it explicitly models that kind of partial observability. And of course, we don't just look at this example. We do tons of experiments. I'm not going to kind of walk through all of them. Basically, the takeaway is that across a wide variety of settings, our method can recover both more accurate predictions in the sense of measures like mean absolute error, and also better calibration in the sense of giving us more probabilistically valid estimates. So that's it for this talk. Thanks everyone for listening, and I'm happy to answer questions here or if you want to find me via email. Thanks.
Great, thanks, Brian. Any questions?
Hey, Brian, great work. This is super interesting and obviously really important. Question on the R0 estimates that you showed earlier for the 3 different locations. Do you get a sense of, is that the R0 before any policy interventions occurred? And if not, is there kind of an inherent contact rate that you can estimate to then use in your model to see, like, if I implemented this policy, this is how people's behavior would change and how we would have different estimates of like R0 based conditional on different types of policies? Yeah,
this is a good question. This is, we believe, before policy intervention, because we also, so I didn't talk about this, but we also kind of explicitly model, right, like the lockdown in each place and the reduction in contacts after that. So this is reflecting the R0 before those forms of intervention occurred. But then also in the paper, we ask questions like exactly this sort of thing, like given that value of R0 at the start of the process, then what happens if you modify contacts for particular age groups in particular ways? And what does that mean for secondary scenarios?
Any more questions for Brian? Okay, if not, Brian, can you please stop sharing the screen? And our next speaker is Jonathan Ferrer-Mestres from CSIRO. And Jonathan will be giving a talk on building explainable and interpretable artificial intelligence for solving decision problems in conservation. So Jonathan, can you share the screen?
I'm not sure if your audio is working, Jonathan.
Yes, the audio is not working. Yes.
Hello, can you hear me?
There you go, you got it.
Yeah? Okay, sorry. Let me share the screen again.
Perfect.
Good, now. Okay, thank you. Hello, I'm Jonathan Ferrer-Mestres. I'm from the CSIRO, And I'm going to present building explainable and interpretable artificial intelligence for solving decision problems in conservation. And this is a joint work with Tom Dietrich from Oregon State University, Olivier Buffet from INRIA in France, and Yerin Shades from CSIRO. So under increasing environmental and financial constraints, ecologists are faced with making decisions about dynamic and uncertain biological systems. And to do so, stochastic dynamic programming is the most relevant tool for determining an optimal sequence of decisions over time. And the mathematical framework for many optimal management of problems, including stochastic dynamic programming, is the Markov decision process model. So very quickly, an MDP is a sequential decision model in which available actions, rewards, and decision probabilities for each state depend only on the current state and not on the states visited and actions taken in the past. And defining an MDP, a Markov decision process model, requires a management objective as well as 4 components: the state space, the set of management actions, a transition probability function, and immediate reward or cost associated with being in a state and taking an action. So for the remainder of this presentation, I will use as an example a problem of recoupling to endangered species, the sea otter and its preferred prey, the northern abalone. And this is a classic conservation problem that was described by Shades in 2012. And the conservation objective is to maximize the abundance of both species over time. The original problem, modeled as an MDP, has 818 states, representing the population of sea otters and the density of northern abalone. And each state is composed by 4 variables, denoting the minimum and maximum densities of northern abalone and the minimum and maximum abundance of sea otters. And managers can choose between 4 different actions, which are introducing sea otters, anti-poaching measures, control of sea otters, and 1/2 anti-poaching and 1/2 control sea otters. So, however, these domains are human-operated domains where MDP solutions provide recommendations to humans rather than applied in an autonomous context, such as in robotics. And the sizes of the solution or policy is in practice difficult to understand and interpret by domain experts, by a human operator. And here on the left, this is a policy graph that shows what action to apply in each state and the probability to transition to other states. And solving this problem as an MDP produces a policy graph with 818 states and up 2 to the power of 818 edges. So in this case, the red nodes are states and edges represent the optimal action to apply in those states. And in human-operated systems, it is crucial that policies can be interpreted and explained to guide decision-making. And we have developed new algorithms to, given an MDP, compute a simpler MDP called KMDP, with a constraint on the number of states, with only K states. So with a small number of states, we hope that we can compute a more interpretable solution to our problem. So this is a simple example of 4 states, of a 4 states MDP with 2 management actions and a computed KMDP with only 2 states and the same 2 management actions with weighted transitions and rewards. And the aggregated state, for example, here the aggregated state SK1 is composed of the original states S1 and S3, and the aggregated state SK2 is composed of the original states S2 and S4. So KMDPs aggregate states with a minimum loss of performance. So we apply our algorithms to the sea otter and northern abalone problem. So for K equal 5 states, our algorithms compute a KMDP, an equivalent reduced AMDP, with only 5 states and only 1% of error, which represents a reduction of 99.39% of the state space. So on the left, we can see the state space representation for the sea otter and northern abalone problem. And it represents the density of abalone and the abundance of sea otter for each one of the 818 states. Each square represents a state, which is also identified by a color. And in the right image shows the reduced state. The right image shows the reduced state space. There are 819 squares representing the original MDP states, and there are only 5 different colors representing the 5 aggregated states. So a color assigned to the square denotes to what abstract state the original state belongs. So when we solve the KMDP, when we solve this KMDP, we come with an easy to interpret solution. So if we have a look at the solution, each node represents an aggregated state. Instead of having 818 nodes, we have only now 5 nodes. And each node represents an aggregated state. And edges represent the optimal action to apply in that state and its probability to transition to another state. So here
Jonathan,
we can
you
see...
complete in next 1 minute?
Okay, sorry. We can see here what the aggregated states include. So as summary, we propose a more interpretable stochastic dynamic programming solutions without losing optimality. And our aim is to increase the take of SDP techniques in human-operated systems by providing easier to interpret models and solutions. As future work, we want to test the interpretability of the proposed KMDPs solutions and address the challenges of visually representing solutions, which is especially difficult for problems with a large number of state variables. Thank you.
Thank you, Jonathan. Any questions for Jonathan? Okay, if not, Jonathan, can you stop sharing the screen? And may I invite Ayan Mukhopadhyay from Stanford University, who will give a talk on emergency response management. Ayan, you can share the screen.
Sure. Can you hear me?
Yes.
Okay. And can you see the presentation?
Yes.
Okay. So I'm going to talk about smart emergency response. It's a very short talk. So what I'll do is sort of try to motivate what some of the challenges are in this domain and what are the broad set of solution approaches that we've come up with. So emergency response basically looks at two problems, which is incident forecasting and resource optimization. And typically, a lot of fields look at these problems in a manner that is orthogonal, but what we try to do is combine them and sort of understand which incident forecasting methods work with resource optimization methods and so on and so forth. So this is a really old newspaper clipping that I found, maybe from the 1930s. And road accidents were a massive problem in the United States. It's been about, 90 years? So you'd imagine that it's largely been solved, but it turns out that it is not the case. This is a rather recent newspaper clipping. And if you if you can read the lines, it says that about 30,000 Americans get killed every year just by road accidents. And then as far as the causes of death under 35 is concerned, this is the leading cause of death. So as far as the large sort of section of the youth of the country is concerned, the death rates are mostly sort of dominated by road crashes. The other sort of problems or emergency incidents that we're interested in are crimes like poaching. So this newspaper clipping tells you that in a span of just 3 years, about 100,000 elephants were killed in Africa to supply ivory to illegal markets. This other sort of trend that we've seen in the last decade or so, this really shy and elusive animal, the pangolin, is being hunted to extinction for its use in sort of the illegal medicine market. And many, many times, crimes like poaching actually subsume other crimes. So for example, illegal fishing often subsumes child labor. So what we're trying to do is to identify problems that cause these sort of emergency incidents to happen. Now, there are many, many reasons for which sort of crimes like poaching and accidents happen, but the ones that are of particular interest to computer scientists are the following. First, these are highly imbalanced resources. So for example, in poaching, you only have a small number of forest rangers who have to patrol really large areas. Second, if you look at how responders are dispatched on scene and in the field, then you'll find that there's a real lack of principal dispatch algorithms. Most of these strategies are very ad hoc. There's also a lack of sound forecasting methods. And then there are a bunch of strategic considerations. For example, in case of poaching, you can sort of dispatch forest rangers, but then the poachers observe where the rangers are and they shift and they commit sort of poaching activities elsewhere. So what we're trying to do is come up with a set of sort of an open source tool chain called StatResp, which stands for Statistical Tools for Emergency Response. So we look at a bunch of sort of data sources: prior incident data, weather data, traffic data, sort of data about the geometry of roadways in case of accidents. And we try to create robust forecasting models, response models, and we try to create these clustering models that can aid forecasting methods. We are doing this in collaboration with a few government agencies, most notably the Nashville Fire Department and the Tennessee Department of Transportation. So here are some of the sort of broad areas that we have, or broad sort of modeling approaches that we've seen to work. Now, forecasting these incidents is very hard because they're dominated by a large number of zeros. So mostly there are no accidents and mostly there are no poaching. So standard regression models don't work, but things like zero inflated regression models and clustering aided forecasting works really well. So for example, you can learn one model for areas that have low incidence and one model for areas that have high incidence. Sorry, Hari, I couldn't hear you.
I think you have 1 more minute if you can wrap up.
Sounds good. Sounds good. Okay, so for allocation, these are really, the state spaces of these problems are really large. So good approaches are to do hierarchical planning, where you sort of break the original, say, a Markov decision process into a bunch of smaller MDPs and then you solve it. Or you do decentralized allocation, where you take a multi-agent approach, but you let each agent plan for itself. For dispatch, these problems are typically modeled as semi-Markovian processes, but even just simple greedy dispatch at times works really well if you use sort of smart heuristics for the other parts of the problem. Then game theoretic models, Stackelberg games work really well to model robustness of forecasting methods. And then you can use normal streaming data models to do online modeling and make sure that your forecasting models are updated as and when new information comes in, or as sort of the environment in which these incidents evolve changes. So we have written 2 sort of papers recently. If you're interested in this broad sort of problems, you can either read the review paper that we have written, or we recently summarized the lessons and challenges that we have learned in deploying emergency response pipelines. I'm happy to talk about these papers or about any of these sub-problems offline. And I also am presenting a tutorial tomorrow at 4:20 p.m. So tune into the tutorial if you want to know more. And I'd like to thank all our sort of collaborators and funding agencies. Thank you so much.
Thank you, Aaron. Any questions for Aaron? Okay. If not, thank you, Aaron. Can you please turn up the screen sharing, and may I invite Elizabeth Bondi from Harvard University, who will give a talk on recent participants utilizing real-time information measuring for conservation and public health. So, Elizabeth.
Okay. Can you still see my screen? Or?
Yes.
Yes. Yes. Can you stop the screen?
Okay.
Perfect. All right. Can everyone see my talk okay?
Yes. Perfect.
Perfect. Thank you so much. Let me also start my timer. Perfect. All right. Awesome. So thank you for the introduction. I'm Liz Bondi. I'm a 5th-year PhD student at Harvard, advised by Professor Milans Tambe. And like Hari mentioned, today I want to introduce this topic. It is my thesis topic, so I'm hoping to give you a very high-level overview of my interests and some of the projects that I've worked on. So jumping right into the overall motivation, as in the title, and as with many of my fellow attendees here today and tomorrow, I'm very much motivated by real-world domains like conservation and public health. And in particular, I think that by integrating low-level sensor information from many of these real-world domains, along with the high-level strategic decisions that we might need to be making in these domains, that we can improve our performance in these real-world settings. Similar to some of the ideas that we've heard today from the previous talk and also from Tom's talk. But in particular, I'm thinking about this low-level sensor information from imagery, for example, drones and satellites, and combining that with these high-level decisions, for example, in multi-agent systems, like using game theory or optimization, again, in these real-world domains. So I'm going to give a few examples from the intersection of these areas. And I'll first start by looking at an example of conservation using drones and game theory. So first of all, conservation drones are used by some of our collaborators at Air Shepherd in national parks. And these drones are meant to try to prevent illegal wildlife poaching from occurring. The way that they do this is they detect 30
thermal infrared imagery, and that is basically looking for heat signatures. So we can look for things like animals and people, for example, at nighttime when poaching typically occurs. So this imagery can be streamed in real time to a base station where we might have a team monitoring this information in real time. Again, this might be happening at nighttime when poaching is typically occurring. And if anyone sees anything, then they can notify park rangers to go and investigate further and hopefully prevent poaching from occurring in real time before any poaching was able to happen. But you might notice that this manual monitoring seems challenging and expensive to have people out all night watching this video. And we also have limited conservation resources. So there are sometimes scenarios where we might have a conservation drone all the way on the other side of one of these large protected areas, and we may not be able to have park rangers respond in time. So this, I will argue, consists of a low-level sensor processing challenge as well as a high-level multi-agent system decision-making problem. So first, focusing on this low-level sensor information. These are two examples of thermal infrared images. They show animals and people respectively, and they also show some results from an automatic detector that we built. And we created a pretty large data set. At least I feel like it was very large, which you can find at this link. It consists of real-world data as well as simulated data that we worked on to try to augment it and improve our results a little bit. So we got some decent results, but let's say that we first replace or augment our monitoring team using this detection system so that it can provide alerts to them. And now for this response question. So again, we might have the case where our park rangers are too far away, they simply can't respond if we do detect something. And so in this case, our collaborators actually experimented with turning lights on aboard their conservation drones. And they found that this, in fact, deterred poaching from occurring. This is an actual video of a poacher running away after Air Shepherd turned lights on. But the problem with what Air Shepherd has done is that they turn the lights on whenever a park ranger is not able to respond. And so that means that eventually a poacher might realize that if the lights turn on, then a park ranger is not coming, and they may have an opportunity to attack and hurt some animals. So that leads us to assume we need to be strategic in this deceptive signaling. And this has been modeled by a Stackelberg security game in previous work by Xu et al. From AAAI 2018. But the problem is that in this previous work, we considered the case, or they considered the case where if there's no detection, then there's no need to signal. So they're assuming perfect detection. And if you do have a detection, then you should do some strategic signaling. Sometimes you signal and sometimes you don't. In our work, we realized that from our work on the low-level sensor processing that sometimes we're definitely going to make some mistakes. And in particular, we might have false negative detections. So there are actually 3 people here in this image, which you may be able to see. Hopefully you can see me circling them now. But in this case, we may still even want to signal sometimes, even if we haven't detected something, because we know that we have this uncertainty in our low-level sensors. And so if you're interested, please feel free to check out our AAAI 2020 paper going through the details of this. But I want to tell you about another example that we are starting to work on. This is ongoing work, so I'm very eager to hear any suggestions or feedback on this. But we're here looking at public health and looking at satellite imagery. And so the particular public health concept that we're thinking about is micronutrient deficiency. And so just as an example, in case you're not familiar with the terms, micronutrients might consist of something like vitamin A, for example. Vitamin A can be found in different foods like carrots and eggs. And vitamin A has some consequences for vision. So if you're micronutrient deficient, if you're vitamin A deficient specifically, then you could become blind at some point if it becomes very severe. And unfortunately, a lot of these micronutrients if you are deficient in them, then it has some negative health outcomes for sure. So in collaboration,
you have 2 minutes more.
Thank you. So in collaboration with some public health researchers at Harvard, we are working on a data set that they collected in Madagascar. It consists of some survey data and some blood sample data from several different ecological regions in Madagascar. And one challenge with this is that in order to measure micronutrient deficiency, we need to measure blood samples because unfortunately, we can't often detect micronutrient deficiency until it gets really severe, until we start seeing things like blindness. And so one thing that you might imagine is we can use some of this survey data that's collected to try to predict whether someone might have micronutrient deficiency or not without using the blood sample data. And this would probably help quite a bit. But the problem is that questionnaire data also can be difficult and expensive to collect and often is only done once every few years. So what we are thinking is that we can use this questionnaire data to inform what satellite data we could use to then predict where people may be at risk of micronutrient deficiency. And this might seem a little out there. So just as an example, one question that you might find in your survey, for example, is did you eat rice? And so then in the satellite data, we might be able to look for rice paddies, for example, and depending on how close you are to that or whether you might have access to it from different means, then we may be able to predict whether there is micronutrient deficiency risk in that area. So in doing so, we may be able to provide more real-time information about where micronutrient deficiency is located. And so eventually, we would like to use that real-time or closer to real-time information to then inform perhaps where we should target intervention resources. So for example, where you might want to focus on encouraging agriculture or reforestation efforts, or even healthcare center deployment. And so just to conclude, again, my overall motivation is coming from these real-world domains. And I hope that I've illustrated how we can hopefully integrate this low-level sensor information with high-level strategic decision in these real-world settings. Please feel free to reach out to me via email or check out my website for more information. And I'd love to talk with you more throughout the conference as well. Thank you so much.
Thank you, Elizabeth. Any questions for Elizabeth? Okay, if not, our next speaker is Theresia Yazbek from Ohio State University. And Theresia will be giving a talk on effects of spatial heterogeneity of leaf density and crown spacing of canopy patches on biodeposition rates.
Hello, everyone. You can see my presentation, right?
Yes.
Okay.
You might want to share the other screen.
Yeah. Okay. Okay. Hello, everyone. So today I'm gonna talk about the TES sustainability on the ecosystem level. So basically, TES works on a sustainability index where the ecosystem can work with the industry, so to have less pollution. So we're gonna work we worked on the trees ecosystem where the trees supply the uptake of the pollution and the demand is coming from the industry. So here's the sustainability index. So what we're trying to do is to increase the supply of the trees by having more efficient design of the trees canopies. So we're trying to increase this index by playing around with the density and the spacing of the canopy, so it increased the deposition rate of pollutions. So we used PALM, which is the Large Eddy Simulation model. It's a well-validated model for micrometeorology, and the PALM has a module for canopy, which modulated it as a viscous medium, and it can capture the effect of the canopy on the boundary layer, the lower part of the boundary layer. So our model was like around 0.5 kilometer by 2 kilometer and with a height of 1 kilometer. So we tried to simulate an industry stack that is emitting some we call it scalar, basically some pollution, and which is hitting a canopy downwind. So here are the input parameters. We input temperature and heat and fluxes, in addition to the scalar concentration. And we had the two different setup of canopies. We had one, a homogeneous canopy, which is basically the one shown in the picture. And we had canopy strips perpendicular to the incoming wind. So we had an empty like canopy strip, then empty strips, then canopy strip, then empty strip. And we used different strip width. We had narrow, intermediate, and wide strip. And as for the density, so that was for the patches. And as for the density, we worked on different densities referred by leaf area index going from 1 to 4. Now, as for the results, so first, here is a picture about like a figure about the scalar flux, the surface scalar flux. So basically, how much pollution is going into the canopy. So here we have two main observations. First, that perpendicular strips were doing higher, like we're having more uptake than homogeneous. So more deposition is going on canopy strips. That's first. Second, the more dense the canopy, obviously, the more we have deposition. But for the same density, we had a higher uptake on perpendicular strips than homogeneous. So why is that? So here is a closer look. So here we are seeing the deposition rate on the right color bar, and then the concentration at the end, and the wind flow. So as you can see, compared, so those are the two perpendicular cases, and here is the homogeneous. So we have a higher deposition rate on the canopy edges. So since we had more canopy edges facing the wind, we are having more deposition rate. So that's first. And second, between the empty edges, we had the wind that is going. So the wind, when it hits the canopy, it goes down and like almost zero, and then it was able to recharge. The same thing happened to the scalar. So at the right, we can see the deposition rate equation. So as you can see, it's the wind speed times the scalar gradient, which is the scalar concentration, basically, because we assume that the concentration on the leaf is 0. So basically, at the edge of the canopy, we had high wind and we had high concentration, where these components coupled together led to a higher deposition rate. So how can we,
one more minute.
yes? So how? Thank you. So how we can interpret that easier? So in for a rough estimation of deposition is basically deposition 1 over resistances. So what we were able to do is to have to add a resistant component, one for homogeneous and one for and one for perpendicular strips, to account for the canopy patches, and which could be added on this easier model like the one for I3 to estimate the deposition rate. So 3 main conclusions: sparse canopies are more efficient than dense. Canopy strips perpendicular to the wind direction are better than homogeneous, and we can add a canopy resistance. So here is just a fast sketch. So if you have like wind coming this way, having perpendicular strips canopies would be more efficient than having a bulk like homogeneous canopy. And thank you.
Great, thank you, Teresa. Any questions? Okay, if not, Teresa, can you please stop sharing? And may I invite Arnav Gautam from Clean Power Research, who will give a talk on mimi.jl, next generation climate economics model. Arnav.
Yeah, thanks. I think I need to allow Zoom to share my screen. Sorry.
You can, right?
Yes, I will have to quickly rejoin the meeting though. I'll be right back.
Manu, are you ready? Can you give the talk now?
Yeah, I'm here. I'm ready.
Yeah, okay, we'll have Manu then first, and then we'll go to Arnav.
Yeah, we can do that. Just give me a minute.
Okay,
Yeah.
start.
Is my screen visible?
Yes.
Yeah. So, hi everyone. I'll just quickly introduce myself and go through what I'm going to talk about today. So, my name is Manu Laria. I'm a PhD student at University of Ghent. I'm working in the Smart Grids group. We are essentially working with a lot of electric vehicle sessions and what happens when electric vehicle charging happens on the grid and what kind of loads they produce. We have worked on load balancing and different kind of prospects. In this particular work, what we are trying to do is we are trying to model the electric vehicle sessions that are observed in the grid, and we are trying to create a synthetic data set. The reason for doing this is the availability of the data sets, which are not easily available for the research purposes. And the second reason being that doing this statistical analysis of the EV sessions data essentially gives us an insight on the consumer behavior, using which companies can have different pricing options for the consumers, and we can have better load balancing, and we can eventually also develop some MPCs for the same. So what we have done here is we have defined a synthetic data generator that essentially models the EV sessions, which are defined by the arrival time of the EV, departure time of the EV, and the requirement of energy for that particular EV. And this SDG essentially models all these three parameters and produces a synthetic data sample. We have divided the modeling into two different parts. The first one is arrival models, and the second one is mixture models for the connection times and required energy. For arrival models, we have essentially taken two different kind of processes, which are based on under the assumption that the inter-arrival times between two different cars is defined by an exponential distribution. Based on this, we can divide two different processes. One is a simple Poisson process, and the second one is exponential inter-arrival time process. We assume that the lambda parameter that defines these processes is dependent on time of the day, the type of day, month, and different parameters. And we can model this using different modeling methods, for example, polynomial regression or simple regression. And based on this, we have essentially defined 5 different types of modeling methods for arrival times of EVs. In mixture models, what we essentially try to do is we essentially try to model the conditional probability distributions of the connection times based on the arrival times and the time of the day. And we do a similar thing for the required energy. Over here, there is a quick overview of the whole process of what we have presented in one of our papers. We essentially take a raw data and then we create these models, and these models can be saved as a list in a pickle file, and then these pickle files can be shared. So these shared files can be used to generate synthetic data samples, which can be used for multiple purposes, such as studying different TV sessions or building policies or new things. Another important thing that we have presented in our paper are the results for the KDE test and KS test results, which essentially define if the generated synthetic data sample is similar to the original real world data or not. This graph essentially shows the results for that, where we see that three of the methods that we have defined essentially perform in such a way that the synthetic data sample is indistinguishable from the real data. A quick note here, the real data that we have used is based on the Netherlands ELAD-NL provider. This is a charging pole provider that essentially also collects data for research purposes, and we received our data from them, and the synthetic data that would be generated would be a synthetic copy of this Netherlands based data. However, if there is another or if there is a EV data set that has been collected in some other place, these models can also be trained on that data to get a synthetic sample that is similar to those data sets. For example, if in US, there is some area where there are a lot of data collection that has already been done. So the company can create a model and share them with researchers without violating privacy concerns.
Manu, you have 1 more minute.
Okay. So to quickly go through the results, these results are also present in the paper that we have recently published. Along with the paper, we also have a GitHub repository, and in this GitHub repository, the code is provided for training the models and synthetic data generation. Along with these, we have also provided 5 different models that we have trained on the ELAD-NL data. So for researchers who want to work with EV sessions data, they can just clone this GitHub repository and generate as many samples as they want. So with this, I would like to thank everyone for their time. And we have published 2 papers on this work. Both of them are mentioned over here along with the GitHub repository. And my name is Manu Lahiriya. Thank you so much for your time.
Great, thanks, Manu. Is there any questions for Manu? Okay, if not, Manu, can you please stop sharing the screen? And may I invite Arnav again to share the screen and give the talk?
Yeah, sorry for the hiccup before.
It's okay.
Okay. Can you all see the presentation now?
Yes.
Okay, great. Start my timer now. Hi, everyone. I'm Arnav. I'm a software engineer at Clean Power Research, but I'm actually here to talk about a volunteer project I'm doing under Professor David Antoff at UC Berkeley. It's Mimi.jl, which is a software platform for the next generation of climate economics modeling. So what is Mimi? Mimi is a platform that allows people to run integrated assessment models. Now, IAMs are a type of numerical modeling that integrates knowledge from different domains in a single framework. Most commonly, this is used for integrating results for physical models of climate change damages alongside the economic impacts that they may have. And IAMs are used to inform a wide range of policy decisions, including those that are dependent on the social cost of carbon. The social cost of carbon is a metric that is used to do a cost-benefit analysis and represents the net economic impact of emitting an additional ton of CO2 into the atmosphere. It's calculated by running an IAM with a simulation of a pulse of emissions and then looking at the economic impacts. This SCC is used to inform decision-making at various levels of government. One example was President Obama's Clean Power Plan, which depended on the SCC to figure out the benefits of the plan. Now, as a result of its usage, the process of calculating this number has attracted attention. In particular, the National Academies of Science called for an open source modularized platform for running the IAM models. The Mimi framework is a response to that call to action. So what Mimi offers is aimed at 3 types of users. There are developers of models. There are researchers who want to run and analyze those models. And there's also policymakers who may want to replicate analyses or understand analyses that were based on these models. Mimi also provides a community that has collaboration between developers and the users of the IAM. It's open source on GitHub, and there's an active forum. Now, the design of the Mimi platform had many considerations. First off, we knew that it wanted to be computationally fast because IAMs are complex models that run over long time spans. But we also wanted to lower the barriers of entry, making it simple enough for novice programmers and also have it work with the pre-existing ecosystem of models out there. What this led to was making a macro-based domain-specific language that utilizes an easy-to-use API built on the powerful Julia programming language. Now, IAM components are modular and they are also specific. And a model is composed of multiple components which may have their own specifications. The way a component is defined is by the parameters it takes in and the variables that it outputs. as well as specific code that computes the variables. Now, for Mimi in particular, we wanted to put structure on what that code could look like, which allows us to abstract away a lot of the concerns that may otherwise plague connecting components together. This is an example of how a component can be defined in the Mimi framework. It makes use of a macro that we have built for def-comp, and it defines a component with the variables that it is expected to return, the parameters that it is taking in, as well as a function which indicates the mathematical formulas that are used to calculate values at every time step. The models are consisting of their components as well as the connections between components. The Mimi framework takes care of everything from storing the data in various data structures, calculating the values at every time step, sending those variables between components, and ultimately giving the results. This is an example of how the model could be defined in the Mimi framework. Now, as you can see, all that is included is setting the dimensions of the model, adding the various components which were previously defined with def-comp statements, and then connecting the parameters that may be of interest. We wanted to make sure that it was easy as possible to access the results of running these models. So as a result, you can use the typical indexing functions to get access to subcomponents of a model, as well as the parameters and variables associated with it. You can also access the data frame format for these for this data. Now, if you want to access the data and have a visual inspection of it, there's also an Explorer capability built into Mimi, which lets you explore in an interactive manner. Now, the models that are run on Mimi are complex, and there's a lot of uncertainty associated with them, both to do with the climate science side of things, but also the economic side of things. And so tools like Monte Carlo simulations are really important in that they allow us to run thousands of trials and sampling into the space, which gives us a better view. Now, running a simulation in Mimi consists of making use of the def-sim macro that we have developed. What it allows the users to do is dictate what random variables they may be interested in, which would be sampled from distributions that are defined in the Julia distributions.jl package. The simulation here would make use of random sampling, but Mimi also has support for more advanced techniques, such as, for example, Sobel analysis. The way a user would run the simulation is simply providing a model definition as well as a simulation definition. And Mimi will take care of everything from sampling those random variables that were specified, connecting those to the parameters that are indicated in the model, running the model, as well as storing the output. We wanted to make it such that you only have to specify what the behavior of the model or the simulation should be, and Mimi takes care of the rest under the hood. However, the API does not, surface those complexities to the user. Going back to how Mimi was designed, we wanted to make sure that we followed the call to action from the national academies to create a modular platform that allowed for transparency and replicability. What that led to was the use of and creation of a custom Julia registry upon which the well-known IAMs can be registered and easily accessed. We also wanted to make good use of package and project environments. So for convenience, these models are registered in the registry and essentially operate as packages with the Julia package manager. It's a simple task to add these for your usage, and the use of environments ensures that replicability is ensured even as models are updated. This is an example of how you may access one of these models. This is the DICE model, which is a well-known model and you can run it. And for models that are used to compute the social cost of carbon, there is also going to be a compute SCC function that returns the SCC at any given year. I wanted to talk a little bit about the recent work we've done.
Now we have
Now,
2 more minutes.
thanks. So over the last year, we've extended MIMI to support composite components. Now, previously, models would consist of interdependent components, but they didn't have any hierarchical structure. This really hindered the vision of the NAS call for a modular platform. Allowing composite components helps teams interchange and test their equivalent components, and also yields more understood models. So this is what a composite component would look like, taking in parameters, feeding them to inner components as necessary, as well as interconnections between components, ultimately returning a list of variables. This makes the process much easier from the user point of view. This is an example of the MIMI fund model, which was revamped to use the composite functionality. And as you can see, it's more hierarchical and broken down into more easily understood components. This required updates to our visualization, which were not previously reflected in the old Explorer view. So what we have here is a revamping of the Visual Explorer, which indicates the hierarchical structure. It's interactive, and you can look at the various components that may be in a composite component. You can click on a subcomponent to view the different variables and parameters that are specific to that composite component subcomponent. And for variables that are and parameters that are along the dimensions, there are also Vigalite-based visualizations that allow for more exploration. So our vision for, I'll just go through this quickly. Our vision for MIMI is to really improve the modeling process by allowing researchers to write papers that are based on IAMs that are open source, transparent, and fully replicable. And MIMI has seen quite a good amount of adoption, both within the models that it supports, as well as the users of it. And I want to acknowledge the groups that are backing this work, and thank you.
Thank you, Anna. Any questions for Anna? Okay, if not, we'll have a stretch break right now, and we plan to gather back here again at 4:55 to have our next invited talk by Ritvik Gupta. So be back by 4:55 p.m. Eastern Time.
All right, so let's get started here. I think that break is over. So we have an invited talk. We invited Ritwik Gupta from Carnegie Mellon University's Software Engineering Institute to give a talk on AI in remote sensing for natural disasters. Ritwik Gupta is a machine learning research scientist at CMU SEI. His research focuses on the intersection of machine learning and health, with many forays into the area of robotics, adversarial learning, and computational logistics. He is passionate about educating people about machine learning and the many cool and unique ways it can be applied to unorthodox problem domains. And Gupta is affiliated with the Defense Innovation Unit and NASA Ames. He is located at the NASA Ames Research Park in Moffett Field, California. And with that, let's have it to Ritwik. Go ahead and share your screen.
Yeah, hey everyone, good to be here. Thanks for having me. Today I'm here to talk to you guys about, you guys can see this, right? Just to confirm. Good, okay. Yep. I'm here to talk to you guys about artificial intelligence and machine learning combined with remote sensing and how that can be used for natural disasters. So like Caitlin mentioned, I'm a ML research scientist at Carnegie Mellon, and I also serve as a technical program manager at the Defense Innovation Unit, without whom the first part of the work, which I'm going to show you, would not have been possible. So I'll just kind of cover, you know, what is possible with AI remote sensing, what has been done, some of our work in AI remote sensing, and then kind of what else is possible and kind of the path forward. Caitlin, I can't see the questions, so if there's any questions, can you please just read them out for me? I'll be happy to address anything during the talk. So.
Sure. So you just want me to interject?
Yep, please interject. Yeah.
Okay, sounds good.
So disasters are bad. I think we all know that. They impact communities in outsized ways, and it's really hard to be prepared for them. They're, you know, anything from floods and fires, earthquakes and tsunamis. It's really hard to be able to detect, respond, and recover from these disasters. One of the most important tasks during response to a natural disaster is actually knowing which buildings are damaged, how damaged they are, and what kind of impact that damage has on that area. So within a few hours of a disaster occurring, right? So a flood or a hurricane or, you know, a fire, there's usually people on site counting how many buildings have been damaged, to what degree they've been damaged, and what to do about it, right? How do they allocate resources? How do they allocate personnel to start recovering and rebuilding that area? That's obviously a very dangerous task. You know, you're putting people's lives at risk. There's down power lines. The fire may start again, and so we want to be able to do this quickly and efficiently without putting people's lives at risk. And again, I say quickly because this is a very time-consuming process. People are literally walking or, you know, driving around from place to place. You can't cover a lot of the area. So one of the promises of remote sensing is that you can see a large area, right? So using satellite imagery, using helicopters or drones or high altitude persistent surveillance systems like Google Loon, et cetera, I can see a large area, and I should be able to now somewhat be able to count what buildings are damaged, how damaged they are, and kind of what's going on the ground. So in situations like this, let's say there's a disaster in this area. So this is actually Mumbai. So this is a part of Mumbai where there's this really famous slum on the left, really affluent area on the right. It's actually part of a larger art series by this guy named Johnny Miller called Unequal Scenes. And let's say we want to be able to plan a route from point A to point B to reach a point in the Dharavi slum on the left there. So it's pretty easy, right? I can go down this alley, I can go right over here. But as soon as you physically on foot hit the actual slums, it's going to get really chaotic really fast. Routing becomes almost impossible because now you're relying on landmarks, you're relying on people telling you where to go. There's no clear structure. But if you look out on top, right, you look down from a remote sensed view, and there's a lot more structure than we were originally able to see. So we want to be able to exploit information like this, right? Information that you and I couldn't possibly see on the ground, but we could possibly see from the air, and you know, give first responders that information and those intelligence products that help them make a better impact of their jobs. So let's talk about kind of what started a lot of this work. back in the day, so this is like 2018, so way long ago, IARPA, which is the Intelligence Agency for Research and Intelligence Advanced Research and Projects Agency, released this huge prize challenge called Functional Map of the World. And what was so cool about this prize challenge was it was kind of one of the first times, it probably wasn't the first time, one of the first times where not only was a remote sensing challenge held to do classification of your standard things like buildings and cars and stuff like that, but also of categories which would be related to disasters. So things like debris or rubble, things like flooded roads. And it wasn't just one place in time. It was very much, let's observe the same exact place over time, right? So for example, you can see a flooded road here observed at, a specific timestamp. And then, 3 years later, we have the same spot, right? Flooded again in a different instance. So it's really cool, right? We can have repeated revisits over the same exact site for these damage and disaster related instances. So this created a lot of innovation. For the first time, people were able to create kind of, time-oriented deep learning models that are able to accurately classify instances of these imagery. And another cool part was this challenge also had the option of a reject class. So if they gave you a bounding box around something that wasn't really a category at all, you were supposed to be able to say that's out of distribution. So tons of good research and kicked off a lot of innovation in this area of combining AI and remote sensing, especially as it pertained to disaster management and disaster response. So really cool stuff. The data set's still available. If you guys go to Topcoder, it's really fun to check out if you guys get a chance. From there, so us at DIU and a bunch of other people had a great idea, right? How can we automatically do this task of building damage assessment from satellite imagery? So, in today's world, so actually right now, so agencies like CAL FIRE, Cal National Guard, and FEMA, amongst, USGS and other agencies, they actually have this kind of prototypical usage where they're using drones, right? So the same drones you might imagine, so RC-26 or a Predator drone, they equip it with like a FLIR, so like a thermal IR ball, and they fly around, right? They fly around the fire perimeter and say, that building is glowing, so that building is destroyed, and that building's not glowing, so that building must not be destroyed. You have a team of airmen, right? A team of intelligence analysts sitting there hour after hour, day after day, week after week, literally just doing this for maybe a small area, right? So they're doing this for the August fire, the Valley fire, et cetera. So we wanted to take their very prototypical, it works really well. I'm calling it prototypical, but I think it can be done better. We want to say, can we automate this process to be a lot faster? And can we do it for a large amount of area instead of a small amount of area that they currently do, right? So that was the basis for this challenge that we called XView2. So XView2 created a data set called XBD, which basically collected imagery for disasters across a large portion of the world, across many different types of disasters. So obviously fires in California look very different from floods or tsunamis in Indonesia. And so we wanted to be representative of that. So this data set is over 850,000 building instances across over 45,000 square kilometers of imagery. So it's absolutely massive. And you guys can go download it today. Critically, we had to work with our first responder partners. So we had over 40 partners that we worked with, from FEMA and CAL FIRE to the North Dakota and Tennessee National Guards. And the critical task to figure out was, FEMA has a specific scale they use to figure out, to rate damage on the ground for residential buildings for hurricanes and floods. CAL FIRE has an entirely different scale to do the same thing for fire damage on all buildings in California. You really can't reconcile those. So we created this thing called the Joint Damage Scale, which is for the first time, and at least in our knowledge, an effort to unify a way to rate damage across many different types of disasters, at least the 5 ones listed here, for remote sensed imagery, right? And so we use this to create this data set called XBD, which is absolutely massive. Here's an example. So the data set consists of pre-event and post-event imagery. So exact same place, just different time. And then ground truth annotations on the joint damage scale. So 0, 1, 2, 3, no damage, minor damage, major damage, or destroyed. And again, we have this for many, many different disasters, many different parts of the world. So here's another example, right? So this is a tsunami in Indonesia. So you can see here pre-event, post-event, the same annotations. And we also created baseline machine learning models that we released to the public of here's a working attempt on top of this data set. Let's go make this better. So we launched this out as a huge prize challenge across the world, ran it for about 3 months with a $150,000 prize pool. And we got over 2,000 submissions that aim to solve this problem. And I wanted to share some of this work with you today. So let me, I'm sharing my whole desktop, right? So you guys can see when I switch slides here or switch screen. Great. So, competitors gave us machine learning models, Dockerized, that ran really well. We evaluated them all. We, had an automated evaluation mechanism where we could quantify their performance on different disasters, on different types of damage. And we did a whole bunch of work over the last few months in conjunction with CalGuard and CAL FIRE and FEMA to have this work for the real fires. So for California, we have many different areas of interest that the National Guard is looking at. Everything from the LNU fire, Carmel fire. I mean, it's not even rendering all of them right now. But what we did was we can apply these machine learning models to give them accurate assessments for this is what building damage, this is how many damaged buildings they are, and this is how damaged those buildings are for large areas, right? So here's part of the LNU fire perimeter, and you can see very precise pixel by pixel damage annotations for a given building at a given spot on that building, right? So in this case, it's either white or red because fire either burns or it doesn't. So these buildings are not damaged and these buildings are absolutely destroyed. But critically, so while it may take analysts a few days to go over this entire area, we can do this in 45 minutes for over 1,000 square kilometers for about 75 cents of cloud compute costs, right? And we can do this en masse for many different disasters, right? So the SCU fire, the Carmel fire, we have the Valley fire by San Diego over here. So here's an example of Valley fire, right? So here's what imagery looks like pre-disaster. We get imagery from post-disaster. You can see things are burned out.
Oh, I think we're not seeing that actually, Ritwik.
Let me try resharing my screen. One sec.
Okay, now we are seeing that. Yes.
Cool. So, whoops, I am all over the place. Here we go. So here we have, our pre-disaster imagery. We have our post-disaster imagery right here. And again, in 45 minutes, we can run a machine learning model to give you very accurate assessments of here are all these buildings. So let me get rid of the polygons. This is what it looked like before the disaster. This is the imagery after the disaster. And here we can accurately tell you that all these buildings were burnt down right here, right? And so we can do this for a very large area. So there's a lot of power in using machine learning and artificial intelligence for the task of disaster response. And we kind of want to encourage you to think about these same use cases. Obviously, it's not the only thing you can do. There's a lot of applications. So things like nowcasting weather. If I'm a first responder responding to a hurricane, it'd be really good to know, which areas of the city I care about are being hit the hardest and where I can go once weather is clear, right? I can't rely on live radar because that means I'm literally sitting there with a radar screen, waiting till I go. It'd be really nice to have a prediction so I can have everything in place to kind of go and respond as quickly as possible. So this is a paper from Google AI on the top here. On the left, you can see this is the current best ability we have, right? So this is the current predictions we have using radar. It's very coarse and doesn't really work well. The middle is the ground truth. So this is what actually happened over Seattle at that time. And on the right is them using machine learning to predict that same weather. And this is all in Tesla, right? So you can see it's much more fine. It's much more accurate on a per minute scale. Whereas the thing on the left here can only give you predictions every hour. So a lot more powerful. And then there's some work on the bottom right there by MIT Lincoln Lab to do this on a distributed basis. It's kind of same kind of stuff. You can do the same stuff to detect and model floods. So here's some work on the right, again, by Google Research, where they were taking, so they actually have this in deployment for India, where currently if there's a flood in India, the government sends out a huge alert to basically millions of people in that flood basin. And they say, there's a risk of it being flooded, please go evacuate. That's crazy. You can't just expect millions of people to go evacuate, especially in India where mobility is low, right? So Google AI and Google Research have been working on this work where they can, on a very fine basis, using physics, model exactly where that water will flow, and kind of how that flood will change over time. And to do this, they had to build their own depth elevation maps using machine learning and satellite imagery. Tons of cool work. Go read the paper. It's fascinating. But now they've been able to, instead of sending alerts to millions of people, they can much more finely target which segments of the population they need to alert in order to go and evacuate, right? Because, you know, now we don't have to send the alert to all of this area. Now we can only send it to parts of the area which are at risk for flooding. And it's quantified now. On the left, there's some work by NASA FDL last year, I believe, where they could do this on the low-cost hardware. One of the, I think, speakers for CompSust, well, Bjorn, and I know Bjorn's on here, also has some really cool work this year about using XPD to model what areas will look like after they've been flooded, even though they've never been flooded before. So tons of cool stuff in this area. And the field is rapidly progressing, right? There's so much you can do. How do we route and plan across a bunch of disaster areas, right? How do we figure out, you know, how many casualties there were in a war, right? Using natural language processing, using Twitter, and, you know, multimodal information there. So there's a lot to be done in this area. And I know I'm running short on time, so I'm going to try and wrap it up here quickly. I invite all of you to come check out the AI and Hater workshop we're hosting at NeurIPS 2020. We have a ton of great speakers. We have a lot more lined up. More on this later, but, you know, people like Phil Salig, who's one of the guys who's leading up all of the intelligence for the fire season in California. Chris, who is leading all of the geospatial stuff for FEMA, and tons of other great guys and girls talking about kind of their work and how you guys can make an impact. And also we're gonna have a ton of accepted papers. These are from last year, but we're gonna have a ton more this year. Again, talking about the application of machine learning in all sorts of hater domains. So I think that's just within time, according to my timer. So let me stop sharing. Any questions, anyone?
I have a question if no one else does. So I remember you were showing some of the satellite imagery of the buildings in California, and it reminded me how like the wildfires will have a lot of smoke in the sky, and I was wondering how you can create a more robust approach to better identify the damage to the buildings when you have the smoke in the way.
So that's a great question. So again, right now you can see that this post imagery is perfect. There's not a single cloud or haze in sight. But in reality, most of the imagery we work with, so you know, this is just for illustration purposes, but most of the imagery that we work with is full of haze. So we have a whole pipeline that can dehaze imagery, but that work is very, again, prototypical. We need a lot more research to figure out how do we train machine learning models to be robust against haze, right? Because, you know, for all purposes, this is all it's doing is comparing the change in pixels from this image to this image, right? And, you know, if it starts thinking that haze equals damage, then we're going to have really bad predictions. So we need a lot more work on how do we make these things haze resistant? How do we figure out things through? So, you know, if there's clouds, like in a hurricane, there's a lot of clouds everywhere because there's a hurricane. We can't see through those clouds for damage assessment purposes. So how do we use, instead of electro-optical imagery, synthetic aperture radar? There's so much more research that is still to be done. And we're continuously finding new ways to tackle that. Does that answer your question, Caitlin? Yeah,
thanks. And then one other question I had was, you had mentioned early on in the beginning about route planning. I forget, I think it was, I don't remember what country you said, but I was curious if you guys have been working on using the satellite imagery after a natural disaster has happened to like real-time warn the emergency response team. Is that what you're talking about?
So that is something that we want to do. That is something that is a thing that's going to be great for the future. So there's some work by Professor Jean O out of Carnegie Mellon. So she's awesome, young professor, really doing a lot of great work using inverse reinforcement learning to basically give responders explainable semantic mapping of how to get from point A to point B, even if there's obstructions in the road. So something like this isn't in production, but it's something like this would be really helpful, right? So if I'm actually a first responder and I want to go from point A to point B and there's a tree in the way, and that was the most direct route, I have no idea now if I go left, if I go right, if I want to encounter floods or down power lines. So having a route, but more importantly, having a route that tells me why that route is correct is going to be critical. So yeah, there's a ton of work in this area. I mean, Jean's work is just a little bit, you know, a small sampling of what's possible. But yeah, this is something that we want to get to. One of the things I'll definitely, you know, impress upon all of you is research is cool and all. Like a lot of this stuff will work in the lab. A lot of this work will, work on a grass student's laptop. But actually getting it to work in the field on an operator's phone, right, involves a lot of work, right? So a lot of work in efficient machine learning, a lot of work that can't rely on the network or a lot of heavy compute, and fundamentally understanding how an operator uses that information, right? So a lot of UX research. So, even if you, do some great research that solves a task on a very controlled data set, the real world use cases is crazy difficult. So.
Yeah, and before we get to our next event, but there's one more question in the chat here for you from Nick. What role does radiation physics play in the approaches you are all taking?
Yeah, so right now, at least in our work, there's no role. But there is a bunch of other work that attempts to use the amount of solar radiation and measuring the amount of solar radiation to figure out deforestation in the Amazon, the reflectivity and all sorts of other things. There is a role that it plays, but not in the work that we're doing. It's not quite radiation physics, but synthetic aperture radar is a form of observation where it's using active radar to hit the ground and come back up. And the reflectivity of that tells you a lot about the world. And we're going to be doing a lot more with synthetic aperture radar as well. Hope that answers your question, Nick.
I just you can go ahead.
I had a quick comment, Ritvik. So I was curious, if you've thought about augmenting some of your data sets, especially the raster data sets, with work that the Humanitarian OpenStreetMap team has been doing. Because this is like a global level team, and they often put out mapping tasks for people to map after a disaster has occurred, particularly in resources deprived areas like Africa and India, and where there's not a lot of good quality map data. And you could they have usually tasks for all of these disasters, ranging across the diversity of disasters. And yeah, just a comment that maybe that map data would be useful for you when you look at raster data and deriving insights.
Yeah, Erna, great point. We're actually in touch with the Dutch Red Cross and the Hot OSM team, and we're going to be presenting a proposal soon. We have to figure out funding and everything to basically integrate damage assessment into Hot OSM. So not only can we get a lot of that data integrated into our everyday workflows, but we can create a lot more data crowdsourced by Hot OSM workers, again, to do a lot more of these tasks on bad imagery, on imagery which is haze or smoke constrained. But if you have any contacts, please get in touch with me. I'll drop my email in the chat.
I'm super happy to do that. I used to work there. Super happy to get in touch and talk to you more about that.
Yeah, I would love to hear more about that. But yeah, that's something that we're exploring as well. Again, utilizing as many data sources as possible, because again, I think multimodal machine learning is kind of the way of the future for a lot of these things.
Great, and awesome. I just want to mention here that that's a good point that Ritik mentioned about putting the knowledge that we apply on very controlled data set to actual work in the field. In fact, that's one part of the panel discussion that is going to happen tomorrow. At the very end of we have a panel discussion where Yosua Bengio, Carla Gomes, and many others will be talking about this. And one of the questions that we have prepared for that is what challenges have they faced or they project to face when the research that we all are doing. If what challenges will be there if we want to take that and put it into the real world and real into field and data sets. So
yeah, actually, a shout out to Berkeley. So Trevor Darrow's lab at Berkeley Bear he's directly tackling this problem of so Mike Laeli and much of his grad students of how do we actually get things to work in not perfect situations, especially when we have as little data as possible. So go check out their work too. Berkeley's doing a lot of amazing stuff.
Thank you.
Awesome. All right, so we're going to great talk, Ritvik, and great conversation there. But we're going to move on to the first tutorial that we have. Super exciting. By Genevieve from MIT, and Genevieve will be presenting a tutorial on Gaussian process regression for environmental modeling. This tutorial is interactive, so get your programming skills ready to go as Genevieve helps us learn about Gaussian processes. So take it away, Genevieve. And you are muted still.
Thanks.
Yep.
Okay. Let me get everything set up. Well, thanks everyone for sticking on the line. I know it's getting late in the day for us East Coasters, but I think this is an exciting conference. It's gone really well. I've been really excited by all the talks. And hopefully this is a little bit of a, I aim this tutorial as being something that you could take away as a practical skill you could use in your problem. So I think there's a lot of people today who've talked about things like time series modeling and spatial data modeling, and this Gaussian processes are a very kind of general model to have in your toolkit if you're doing any kind of work with spatial or temporal data. So I think this will be useful to a lot of people, I hope. And in the spirit of that, I think it will be, we're kind of a small group here. It's late in the day. Let's ask, if you are confused about anything, please ask questions. Please be as interactive as possible, because I think we'll get the most out of it. Okay, so I guess just a bit about me and who I am. So I'm a PhD candidate in the MIT's ECS department. And I actually have a joint appointment. I'm in something called the MIT Woods Hole Joint Program, which means that I have I have feet both in the Computer Science and Artificial Intelligence Laboratory at MIT, and also I have an appointment at the Woods Hole Oceanographic Institution down on Cape Cod here in Massachusetts. And the Woods Hole Oceanographic Institution is this awesome place with scientists who are interested in asking kind of biological, physical oceanography, all the questions you could imagine asking about the ocean. And so I try to use this position to do interesting work, both kind of in fundamental methodological research for machine learning, but also in applications to ocean science and climate and weather forecasting. So some of the research areas I'm interested in, I just wanted to put these up here in case people wanted to talk to me afterwards, or if we have any overlapping interests. I do a lot of sequential decision making, specifically looking at POMDP models, which have come up a couple times today, which is exciting. Bayesian inference, uncertainty quantification, and reinforcement learning are all things that I care a lot about. And then I try to I've applied these ideas in areas like climate and weather forecasting, which we're going to talk a little bit about today, volcanic and gaseous emission systems, and underwater species distribution modeling, with help from my advisors, John Fisher and Nicholas Roy at MIT. So the first thing I want to do before we go is get everyone to download the demo. And this is going to take a little while to download. So if you could get it started now, hopefully by the time I'm done talking, everything will be set. So this link will take you to a Google Drive folder, which you hopefully are not able to edit. Last time I did this tutorial, someone deleted the files and it was a huge disaster. So hopefully don't delete any of the files, but you're going to need to make a copy of it onto your own machine. Yeah, so thanks Bjorn for putting the link up. Either download it and re-upload it to your Google Drive or make a copy directly onto your Google Drive. You're going to want this in your Google Drive. Because we're going to use Google Colab as a way of running the code, which should kind of get rid of any dependency issues on different operating systems. So yeah, I guess while I'm talking, make sure that starts running, and feel free to look at it too while I talk. I think we'll have some time at the end to go through it together, but hopefully a self-explanatory notebook. So I'm going to start by talking about environmental data and why we care about environmental data. And I think we've seen a lot of different examples in the talk so far about what kind of data comes up in environmental applications. So we have air quality and water quality data. We've had people who've gone out and tried to measure pollutants and chemical dispersion in the environment. We have weather and climate data. So the Earth has this, we have this incredible system of satellites and sensors in situ that monitor atmospheric conditions in the Earth, temperature, winds, moisture, precipitation, to do weather and climate modeling. We have the ability to detect things like extreme events, storms. From satellite imagery, we can detect things like forest fires we just heard about. So there's a lot of kind of interesting remote sensing and imagery data that we deal with in the environmental domain. And some of this data is multimodal. You can use synthetic aperture radar, you can use image data, you can use other spectral modalities of satellites. There's a lot of kind of interesting multimodal data that we can use. I work with people who study the ocean dynamics by putting little floaters into the ocean and watching where they go, watching the Lagrangian dynamics of floaters. Vegetation monitoring from satellite data. This is actually something really cool. I talked to a bunch of climate scientists last semester, and vegetation modeling is actually one of the big uncertainties that we have in long-term climate modeling. So trying to understand the impacts of climate change and increased CO2 in the atmosphere on how vegetation and plants and algae in our environment operate is something that people are really interested in. And so modeling the distribution of vegetation in the world is something that's of interest. Wildlife monitoring, we saw lots of examples of that today, and earthquake magnitude. So there's lots of different kinds of environmental data. And there's also different questions that we might care about asking of our environmental data. So the real focus of this talk is how do we think about the correlations and associations and relationships between different data modalities and use these to lend predictive power in regression settings. We might care about doing trends and forecasting. We're going to talk about a little bit of that today. And then I'm not going to talk today about planning, uncertainty. Well, I'll talk a little bit about uncertainty quantification, but planning and adaptive sensing are things that we care about doing with environmental data. And we really need good models to base plans and adaptive sensing plans on. And so today we're going to focus on the modeling part of kind of the full data pipeline that Thomas Dietrich explained. So what's special about environmental data? I'm going to call out 3 different things that I think are special. And the first thing that I think is really interesting is that, unlike a lot of different sensing modalities like camera data or image data, we actually have really good science models of environmental data. So scientists in different domains, they spend their entire life studying kind of how do clouds form or what is the mixing in the layers, in the boundary layer of the ocean. And all of these models have kind of succinct expressions as systems of dynamical equations. And I think this is a really powerful thing that we should be taking advantage of when we work in these environmental data domains whenever possible. So just these are complex systems that we actually have, scientists have models that start to tackle portions of those systems. And understanding how we can use those as machine learning practitioners or other scientists, I think is really important. Another thing that's really special about environmental data is strong spatial correlations. And this is something you can't ignore if you care about modeling environmental data. So this is a measure of ozone, a pollutant, like low atmosphere ozone at 3 different locations in Massachusetts. And you can imagine that, if I'm trying to predict the ozone levels in Roxbury, I care a lot about what are the ozone levels at the Blue Hill Observatory or the Lynn Water Treatment Plant, because spatial correlation is one really strong signal I have for making predictions with environmental data, and that's going to be the main focus today, actually. And then we also have temporal correlation. So if I care about seasonal ozone distribution at one location, it doesn't look, kind of like a random collection of concentrations. You have strong seasonality often in environmental data, periodic trends, and so you want to be able to think about how do you model those kind of temporal correlations in data as well. And so just to summarize, environmental data, what do I think is special here? I think we have correlations in time that we need to deal with. We have correlations in space. We have scientific models that we need to think about how to incorporate. And then there's a lot of other kind of just methodological questions for statisticians or machine learning practitioners. One is that we often don't get to run controlled data studies. You can only watch what the Earth does. You can't, measure the counterfactual where you decide what to intervene and see what would happen differently. I think we often care a lot about trying to verify scientific hypotheses from data. So we need to think about how to do that. And uncertainty quantification often plays a big role in that. And I'll talk about that too. We have large data sets. I actually think that the world, there's certain aspects of the world that we undersample. Like I think it was mentioned that we don't have species distributions for lots of species, but we actually have huge earth and ocean monitoring systems, sensing systems that are in place on gathering huge data sets. So I think we need to know how to deal with them. We have lots of different heterogeneous data modalities. And so I think it's a very rich data environment with these interesting properties. And it requires special thought to think about how to build models in this setting. So the focus of today is going to be regression in space and time. And so regression is this definition you could look up in a textbook. It's a statistical process for estimating the relationship between a dependent variable like time or space and one or more independent variables like temperature or precipitation or carbon dioxide concentration. And we're going to specifically look at the case where the independent variable is, where the regressed variable is time or space, and what we care about are environmental conditions. And Gaussian process models are kind of general to many settings, but we're going to look at spatial temporal trends. And so I have 2 examples of figures up here. On the left, we have a spatial field, and on the right, we have a temporal trend. And there's a couple things that I want you to notice here. One is that these signals are actually very strongly correlated in time and space. So if I'm on the right here and I'm measuring carbon dioxide concentrations from 1990 to 2000 or 2100, there's some seasonal variability in the data you can see, and there's this overall trend. And so regression is going to allow us to kind of capture the effects of both of those and make predictions going forward. And in this case, in this picture, it allows us to quantify the uncertainty in those predictions, which is powerful. And then on the left here, we have global average precipitation over the Earth. And something that's really neat to see is that there's all this correlation structure in the data. So if I have some sparse measurements of precipitation at grid cells in the world, and I want to make predictions about what does precipitation look like in other areas, there's this band along the tropics where precipitation is highly correlated. And so you could imagine trying to make predictions in this direction along the equator. You might be able to do a very good job with some sparse measurements. And then there's a different direction, kind of latitudinally, where correlation falls off really quickly. And if I have a sample of precipitation here, it tells me almost nothing about what precipitation is right above it. And so there's this interesting kind of non-stationarity in the way that our data are correlated spatially often. And that's going to be important for modeling as well. And the main intuition that we're going to build on, Gaussian processes build on, and we're going to build on for the rest of this talk, is that the correlation between some observable at two different points, so precipitation on the equator and precipitation in North America at some point in North America, is a function of the distance between those two locations. And that's really the core center point of Gaussian process regression, is that you can think about if you have some observable quantities and you're trying to do regression of that quantity at other locations, there's correlation between the data that you've observed and the data that you want to make predictions of that's based on kind of the relative locations of those points in space. And the key questions we need to think about is, how do we measure distance? How does correlation fall off with distance? Does it vary differently in different locations? As I mentioned in this example, precipitation is highly correlated along the equator and maybe not correlated in other directions. And so those are all aspects we need to build into our models. But the core kind of insight is that when we're trying to make predictions with spatial or temporal data, we can leverage this idea that there are spatial and temporal correlations. So are there any questions there with the setup and maybe what we're trying to do? I'll say this last slide and then I'll pause. So kind of the objective that's going to ground us for this talk and the exercise that we work through in the coding example is that we have some partial observations of temperature. So you can imagine I have a bunch of temperature sensors across the Western United States. They're measuring temperature. I get this sparse grid and I want to produce this dense grid of temperature measurements where I'm performing regression in order to predict temperature at different points in the world. And actually the really cool thing that you can't see on this figure, but you're going to get out of a Gaussian process model is you can produce this, you can predict temperature everywhere in the world, and you can also predict the uncertainty that you have in those temperature readings, which is really powerful. So any questions there before we kind of dive more into the details of how we're going to build this model?
So this is just over space, not time, right?
Yeah,
okay.
Yeah, that's true.
Are there regression models that do both at the same time?
So Gaussian processes, yeah, will allow you to do both, which is really neat. You can think about, kind of if you have an independent variable that's either a point in space or a point in time, or you can think about a point in space-time. So it's going to allow you to kind of do any of them. We're just looking at space and time separately in the coding example and today, but you can actually build a model that predicts kind of space-time trends too, which is really neat. Yeah.
In the chat here, we have a question from Aaron. Do you have any tips or tricks for visualizing those correlations? I would second that question.
Where? Oh, let me see if I can find the chat quickly. So visualizing these correlations. Yeah, I wish there's a figure that I've shown that I've had in previous slides I don't have today, but I mean, you can do something literally where you just, you look at some time series of temperature for one point like Boston, and then a time series of temperature for a different point like Pittsburgh. And you just compute the correlation between those two time series. And you plot that as like a graph edge between those two locations with some color that says, this is how correlated those two locations are. And you can imagine doing that for every 2 points in the world, which would not scale well, but some subset of points. And you can get a graph that's kind of colored by how correlated different points in space are. And that's something that people actually use in climate modeling, which is really neat, that or weather and climate modeling, if you're trying to predict the weather in Boston, there's actually strong correlations between the weather in Boston and I think some location off the coast of New Zealand. just the way that the atmospheric dynamics work. And that's hard. I mean, you can see that in some models, but you can also just like look at, when temperature goes up in Boston, does temperature tend to go up or down in New Zealand? And so these timed-like correlations, you can build graphs between different points in the world and try to visualize things that way. And we're going to talk about some kind of simpler models of correlation too as we go through this. How do you think about how correlation will vary as you kind of move further away from locations in space? Does that answer the question? Yeah. Cool. Okay, so we're going to start off just by trying to think about how we would build a really simple model. So we have 2 points on this grid. They're actually not on this grid, but Boston, temperature in Boston and temperature in Pittsburgh. And we want to build a probabilistic model. We have a sensor that we've placed in Pittsburgh that measures temperature, and we want to kind of make predictions about what will be the temperature in Boston based on readings of that sensor in Pittsburgh. And this kind of the basis of this simple 2-variable model is what we're going to use to kind of extend and build the whole complexity of Gaussian process modeling. See if I can advance slides. And so the framework that we're going to work with is multivariate Gaussian distributions. And the claim here is that, the correlated multivariate Gaussian distributions provide us a principled way of performing regression and quantifying predictive uncertainty. And I think it'll be clear what that means, but we're going to put ourselves in the space where we're going to model the probabilistic model we're going to use are multivariate Gaussian distributions to model the relationship between temperature in Boston and temperature in Pittsburgh. And so just as a reminder of what a multivariate Gaussian distribution looks like, so if y1 is the temperature in Boston and y2 is the temperature in Pittsburgh, y is this random vector, that's y1 and y2, and if it's distributed as a normal Gaussian multivariate Gaussian distribution with some mean vector mu and some covariance matrix sigma, then it has this probability density function, which is not as important as just like kind of having this visual of what the joint density of these 2 random variables look like. So you could imagine that this mean vector tells you if I randomly observe temperatures in Boston and Pittsburgh, what's kind of the average that's going to be centered around. So the average temperature in Boston, this is 0, and the average temperature in Pittsburgh, 0. But you can imagine this mu could be, any value here. So mu tells you kind of where is the center of this random vector. And then the covariance matrix tells you what is the spread of temperatures around that center. So how variable is temperature in Boston? How variable is temperature in Pittsburgh? And then how kind of correlated are those 2 random variables? So if temperature in Pittsburgh tends to be high, how high does temperature in Boston tend to be? And so I guess multivariate Gaussian distributions can model data that look like kind of any of these data clouds. So if you imagine the x-axis here is temperature in Boston, the y-axis is temperature in Pittsburgh. All these distributions have a mean. These can all be represented as a Gaussian distribution, a multivariate Gaussian distribution with a mean vector of 0. They're all centered around 0, and then different covariance matrices. So the covariance matrix here would kind of encode this idea that they're not correlated random variables. The covariance is 0, and so you have kind of independence between temperature in Boston and temperature in Pittsburgh. They're not at all predictive of each other. Whereas if you start to increase the correlation or the covariance between the 2 variables in our multivariate Gaussian model, you end up with more and more tightly correlated observations, where if temperature in Pittsburgh is higher than average, temperature in Boston will be higher than average as well. So multivariate Gaussian distributions allow us to build a probabilistic relationship between data that has some specified correlation. And so the kind of understanding question here is, if you were trying to describe the relationship between temperature in Boston and Pittsburgh, what graph might be, which correlation, which covariance of a multivariate Gaussian distribution might be the right choice. And if you were trying to describe the correlation between temperature in Boston and Brisbane, Australia, how would that choice differ? And so, I guess asking people to answer questions at a 5 p.m. tutorial might be too hard, but I think intuitively for kind of building this whole modeling framework on this idea that places close in space are correlated with each other, Boston and Pittsburgh, if it's hot in Boston, it's probably also kind of hot in Pittsburgh. They're going to fit kind of into this multivariate Gaussian distribution with high covariance or high correlation, and potentially Boston and Brisbane. I tell you what the weather is in Boston, it tells you nothing about the weather in Brisbane. Maybe you'll fit more into this low covariance or correlation multivariate Gaussian distribution. Any questions here with kind of like how this modeling setup works for two random variables? Okay, neat.
There is one question in the chat here. What was C here again? What is the variable C?
Yeah, so C is it's the correlation between the two random variables in this example. So it maxes out at 1, and correlation is just normalized covariance. So kind of I'm using those terms interchangeably, but the covariance can go from 0 to infinity. It's not bounded. Correlation is from 0 to 1 because it's a normalized version. And so when correlation is 0 here, you see just no relationship between the two random variables, and when correlation is almost 1, you have almost perfect correlation between the two random variables, or perfect correspondence. And the important thing is that these dots represent samples that you would draw from a multivariate Gaussian distribution with a correlation or covariance specified by this covariance matrix. So if I put 1s into this covariance matrix as the covariance between my two y1 and y2 random variables, and then I'll get a PDF that's long and narrow. And then if I draw samples from that PDF, I'm going to get samples of temperature in Boston and Pittsburgh that look like this. Okay. So we're going to kind of dive into this, like what we can do with this model. So I'm going to pretend that I have a magical oracle that hands you a multivariate Gaussian model for the temperature in Boston and the temperature in Pittsburgh. They tell you that it's a multivariate normal distribution with a mean vector of zeros, which is maybe a terrible model for temperature, but we'll work with it. And a covariance matrix that looks like this. So 1s along the diagonal. This is the variance of each random variable, and then along the off diagonal here, you have the covariance of the two variables. So it's a high number, close to 1. These are highly correlated random variables. And you can see that this model kind of, if we drew samples from this model, it would look like, something like this. So this model, this is representing an equiprobability contour of a multivariate Gaussian distribution of temperature in Boston and temperature in Pittsburgh. And now I remember I had put a sensor in Pittsburgh and I don't have a sensor in Boston. So I've produced this model of the joint distribution of temperature in Boston and Pittsburgh. Now my sensor in Pittsburgh gives me a reading and it tells me that temperature is -0.2 here. And the question that we're going to ask ourselves in regression or probabilistic regression is, conditioned on this observation of temperature in Pittsburgh, what prediction do I make about temperature in Boston? So I'm going to look for the conditional distribution of y1, my temperature in Boston, conditioned on some observed value of y2, the temperature in Pittsburgh. And the neat thing about multivariate Gaussian distributions is that distribution is available to you in closed form. Because you've kind of produced this model of the joint y1 and y2, you can observe what is the conditional distribution of y1, given that y2 was observed to be 0.2. And so I can do that by, you look at this little horizontal slice of temperature, given that I observed temperature in Pittsburgh was here, temperature in Boston is going to be along this slice here. And it gives me a Gaussian distribution with some new mean and some new variance. That's my predictive distribution of what temperature in Boston will be conditioned on temperature in Pittsburgh. And so this kind of intuition that we built here of like, if I gave you temperature in Pittsburgh, I would get this new Gaussian distribution for temperature in Boston is encapsulated in these conditional probability equations for Gaussian random variables. And these, the form of these equations is not important, but just that you know that they exist and they exist in closed form. So if you define some joint Gaussian model between your random variables, and then you observe some subset of them, YB, and you want to ask about what is the conditional distribution of YA, given that I have some observations YB. The conditional Gaussian distribution is another kind of lower dimensional Gaussian distribution with a new mean and a new variance. that is given by these equations. So I can kind of come up what is the form of this red Gaussian for my prediction of temperature in Boston using these two equations.
We have a question in the chat. Is there a type of correlation between Pittsburgh and Boston that GPS, I think that it was GPS, could not pick up on because of their Gaussian, Gaussian processes could not pick up on because of their Gaussian assumption?
Yeah. So I think, this choosing to model your data as a Gaussian, multivariate Gaussian is a specific choice. And I don't have a good picture, but if your data didn't look anything like this, if they were some like kind of squiggly S, you could try to model that with a Gaussian, but you'd end up with a Gaussian maybe with zero correlation that couldn't capture this nonlinear or non-monotonic correlation structure between temperature in Boston. And this would correspond to something like during the winter, temperature in Boston and Pittsburgh are highly correlated. So in low temperatures, maybe you have high correlation, and then maybe they're inversely correlated in the summer. It's not a very realistic scenario, but you could definitely come up with correlation structures that don't look like this and aren't modeled by kind of a nice linear relationship. And kind of more generally, a monotonic relationship. If your variables have a monotonic relationship, this can work really well. If your variables have some crazy non-monotonic relationship, multivariate Gaussians are usually not a good model. And just to kind of solidify our understanding here, hopefully, if I give you a new task, I ask you to model the temperature in Boston, given that I have an observation of the temperature in Detroit, and someone hands me a new multivariate normal model, which is a new covariance matrix, where this number 0.5 is smaller than 0.9, indicating that these are less correlated random variables. Then kind of the joint distribution looks like this. It's this wider ellipse and conditioned on a specific observation in Detroit. So I observe again that the temperature in Detroit is -0.2. I have a much wider, the resulting Gaussian that I have about temperature in Boston. Again, it's a Gaussian random variable with a different mean and a much wider variance, indicating that because these are not as correlated as random variables, the information I got by measuring temperature in Detroit is not as impactful on my estimate of temperature in Boston. And so this is kind of like if I gave you just two cities in the world, this is a really flexible framework for making predictions about unobserved quantities based on their correlation with the quantities that you do observe. Okay, so any questions there? Just a demo check. Is everyone able to download everything okay? Nothing, everyone who wanted to could access the data. Okay, I'm gonna just keep going before we get to it. So what are the limitations of this simple 2D Gaussian model? So the first question you might ask me is, I gave you these like oracle covariance matrices and mean vectors, and where do they come from? If I have a new city, if I now give you, I don't know, Tempe, Arizona and Tallahassee, Florida, and I want you to come up with a probabilistic model for those two cities, you need to come up with this covariance matrix that describes the relationship between the two and a new mean function. And then the other question you might ask is, how do you expand this to include more locations? So I have lots of sensor measurements. They're coming online. Every once in a while, I'm getting a new sensor measurement and a new city, and I want to make predictions. I might not know ahead of time what cities I want to make predictions about, but I might want to query a location, an arbitrary location, an arbitrary city, and ask about what is the temperature of that based on all my sensor measurements. So how do we expand this model to be more flexible, include an arbitrary number of cities, and have kind of more flexible dependent structure, I guess, between this encoded in this covariance matrix. So how we're going to do that is we're going to introduce Gaussian process models, which are a super kind of intuitive step from, if you understand multivariate Gaussian distributions, it's like exactly the same thing. But instead of having a covariance matrix, we're going to introduce a covariance function, which just given any 2 points in space will return the relevant entry of that covariance matrix. So it's going to tell you what is the covariance between or correlation between these two cities. And a mean function, which does the same thing for the mean vector. If I give you a city, this function is going to return the relevant entry in the mean vector for the multivariate Gaussian. And this is going to allow us to kind of extend this model to arbitrary locations, because these covariance functions and mean functions are going to act as the oracle that provides us the covariance matrix in our multivariate Gaussian model. And then, yeah, moving from multivariate Gaussians to non-parametric Gaussian processes is as simple as just kind of like letting the number of cities go to infinity. So if you can understand the multivariate Gaussian case, everything is good. Okay, any questions there on what we're kind of aiming to do? Great. So the first question, and this is like the most important modeling decision that you make in a Gaussian process model, is how do you measure kind of distance for the sake of prediction, or how do you come up with this? I give you 2 points in space and you tell me what is the correlation between those, or the covariance between those 2 points in space. So for example, this can be a really complicated and a really subtle question. If I wanted, instead of temperature in Boston and temperature in Pittsburgh, I wanted the concentration of some pollutant at this point along the river and the concentration of some pollutant at this other point along the river, I could do the same thing where I come up with a covariance matrix for those 2 points, but I need a way of measuring, you know, how, as I move along the river and I move kind of further away from the point where I have a measurement, how does my correlation covariance vary? And it might be kind of complicated. This is a circuitous river. Maybe I have to measure distance along the river. Maybe correlation falls off as I move along the river. Maybe there's turbulent regions. Maybe there's laminar flow regions. So the real question that we need to ask is, you know, given 2 points in space, what is the correlation between the observable quantity that I care about at those 2 points? And for Gaussian processes, we make actually a really simple assumption. The simple assumption is that relationship can be encoded by something called a covariance function. So a covariance function quantifies the covariance between 2 observations, two observables, temperature, for example, yi and yj, taken at 2 locations, xi and xj, as a function of location. So this basically, it's a function that you input 2 locations and it spits out what is the correlation, or sorry, the covariance of those 2 of the observable random variables. And in a Gaussian process, we often assume that it takes a really simple form. So the most common covariance function that people use is this squared exponential or radial basis function covariance function, where it says that if I give you 2 points, xi and xj, then the covariance between the temperature at xi and xj is going to fall off as those 2 points get further and further apart, and it's going to fall off in a specific way, this kind of exponential decay. So the high point here is where xi equals xj, the points are right next to each other, and then as those 2 points get further and further apart, the covariance between the temperature or whatever observable you care about is going to fall off in this way. There's also periodic covariance functions, which encapsulate this idea that, you know, if our x's were in time, if I was trying to predict temperature on July 14th, 2010, if I try to make predictions further and further away, the temperature is going to become less and less correlated with my temperature that I've measured at July 14th. But there's going to be these peaks in the covariance function because, you know, when I get to July 2013 or 2014, the seasonality is going to induce correlation or, covariance structure between those 2 points. So these are kind of 2 commonly used kernels, but there's a whole zoo of them, zoo of covariance functions. And this is the modeling choice that you make in a Gaussian process. It's really the main modeling choice that you make, and it encodes this idea of how does correlation fall off in space. So then, I guess, how do you use this? So now you've made a choice of covariance function, and now you want to return back to our Boston-Pittsburgh temperature model. Instead of having to query an oracle to get that covariance matrix, we can now just evaluate our covariance function at the location of Boston and at the location of Pittsburgh, and it's going to give us the relevant entry in our covariance matrix. So now, if I give you any arbitrary collection of cities, you can populate this, and you know their locations, you can populate this covariance matrix and like build a multivariate Gaussian model. Does that make sense? Awesome. And so that's kind of the whole secret sauce, actually, is because we have this covariance function, which is super flexible and allows us to build multivariate Gaussian models for any collections of points in space, given that we know where they are. And we also we need the ability to we need a mean function that will tell us, again, the mean of our multivariate Gaussian for any arbitrary point in space. nothing stops us from building kind of arbitrary multivariate Gaussian models where for any collection of cities that I want and any collections of points that I want to make predictions at, I can construct this covariance matrix, I can construct this mean vector, and then I have a multivariate Gaussian distribution that represents all of the relationships between my random variables, and I can make predictions in the same way that we did for the 2D case. So if I observe some subset of them, I can compute the predictive distribution of a different unobserved subset. And so a Gaussian process is just a collection of random variables, any finite number of which are multivariate Gaussian distributed. So this, I think a Gaussian process is just this idea that because the covariance function is so flexible, it allows you to construct this model for any points in space. You can just, for any finite collection of cities you might care about modeling, you can construct this multivariate Gaussian model. And it's fully, the only model parameters that you have to specify here are a mean function and a covariance function. And there's some, caveats on what kind of covariance, what the properties the covariance function must hold, but in general, you usually just choose from the zoo of covariance functions that describe correlation structure in space. And so what do the predictions of this model look like? So how do you actually do prediction in a Gaussian process? That means exactly the same as in the multivariate Gaussian sense. You have a bunch of locations that you've taken measurements at. You have a bunch of locations that you care about making predictions at. So you can think about like an evenly spaced grid along this axis. You form a big multivariate normal model of those things. You build the covariance matrix using the covariance function based on the locations of points and the mean vector using your mean function, and then you can make predictions. So given I have observed temperature here at -1 and here at 1, for every point in space, I can make a prediction of what is the mean and what is the variance of temperature at this location 0. And that's what I've done in this plot and this plot and this plot. And you can see that as I add new measurements to my model, new observations, the predicted mean starts to kind of, I guess, concentrate around those observations, and my predictive uncertainty has to do basically as I move away from points that I've seen, because I have this assumption that correlation is falling away in space. The observation here is correlated with all of these points, but it's not as strongly correlated as the observation here. So I have more uncertainty here than I do here. And so these are the kind of plots you'll see for multivariate, but it's this really powerful regression technique that allows you to kind of, make predictions about the mean and the uncertainty at any point in space, given I have observations at any other points in space. And it's leveraging this covariance function, which is returning, covariance for any between the things that I've observed and any arbitrary query point. And so you can think about, this was a one-dimensional example of regression. This is a two-dimensional example of regression. If I want to predict temperature, then I have sensors that I've placed all over this room, and they've given me observations, then you can see that this is the mean that I've predicted over the whole room for temperature. And this is the variance of my predictions of temperature. And unsurprisingly, the variance is quite high, or the uncertainty is quite high in these regions where I don't have any sensors, because again, it's this, my correlation is falling off in space. And so the observation here is correlated with these sensor observations, but as I move further away from anything I've seen, my uncertainty grows. And so the tune that you have as a modeler using a Gaussian process model is basically you tune this covariance function. So you determine how correlation falls off in space, how quickly it falls off, how slowly it falls off, does it have a periodic structure? And the most common kernel that people use is this squared exponential kernel. I'm sorry, I'm using the word kernel. It's completely synonymous with covariance function. But it has a parameter L, which is kind of the big tunable parameter here. It's the length scale. And so it determines how quickly that Gaussian or that exponential decay of covariance falls off as you move away from points that you've observed. So for very small length scales here, like 0.3, your correlation or your covariance falls off very quickly in space, and your uncertainty grows very quickly as you move away from observed points. And you can see that here. As you increase the length scale, things become smoother, because I'm saying basically that my correlations hold further and further out as I move away from points that I've observed. And as you make it the length scale huge, kind of any prediction that I'm making here is super correlated with the thing I observed here, 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 and here. And so my uncertainty is really low. And so this length scale is a tunable parameter that you can use to say, yeah, given the actual.
Oh, we lost your audio. Okay, your audio's back. Oh, yep, you're back.
Yeah, can you hear me again? Sorry, my hands just died. There's a whole zoo of different covariance functions that you can use. I'm not going to go through them, but they're all like a modeling choice that you make that tells you how quickly do correlations fall off and how smooth is my function. And so, yeah, I think with that, we have like maybe a little less than 10 minutes to go through the tutorial. And so I'll do that with you, hopefully live here. Let me stop this presentation and pull this up. So if you have the tutorial, you should be able to open it. I guess, could you raise your hand or your virtual hand if you have the tutorial and are going to go through it? Feel free to just watch me if you don't want to go through it, but nice. Okay, so I'll at least have some people. So if you run this, it's running in a Google Colab notebook, so it's running on a Google server. So you need to just start by installing these packages, and the Gaussian process library that I'm going to use is something called GPy. There's a bunch of different Gaussian process libraries. One is in scikit-learn, right in Python natively, but I like this one, a little more flexible, and I've used it in the past. So these will just install the relevant packages. It should just take a few minutes. I guess I could do it live.
And we'll try to go through this in like 5 minutes or so, if that's okay, Genevieve.
And then the example that we're going to work on is this seasonal rodeo data set. So this is actually a problem that I worked on this summer. How do you do subseasonal weather forecasting? Let's see if I can open this. So this is the US Department of Reclamation put on this big competition to see who could do a good job of forecasting precipitation and temperature in the Western United States. And one of the models that we considered was actually a Gaussian process model. So this is real data from the competition, temperature and precipitation data, and we're going to see how well we can do at interpolating from sparse measurements based on Gaussian process models. So then you can, run the relevant imports, and then the only kind of complicated bit here is that you have to get the data accessible via the notebook, and it shouldn't be too hard. If you run this here, it will give you a prompt to log into your Google Drive account. You have to provide an authentication code, but then this notebook, Colab notebook, will be able to access the files on your Google Drive. So I'm not going to run that again, but you should be able to run that. Then we can read in. No, I do have to run that again. So it will take you here. You have to authorize your Google account, copy this authentication code, paste it back in here, and this will mount the data onto this remote cluster. And maybe I'll just scroll through it here as we.
Yeah, Genevieve.
Just to show where we're going. So we have, this is the data that we're going to look at. So this is temperature, precipitation, and temperature data. I gave you kind of all three. You have max, min, and precipitation data that you can visualize in the Western United States. We're going to start with a sparse data set. So we're going to start with sensors that are only positioned at these locations. And we're going to try to make predictions using Gaussian process regression about temperatures at kind of all the rest. So these are the held out ground truth temperatures at different locations in space. We're going to try to predict them based on these very sparse sensor measurements. So maybe this is done. Mounted, so I'm going to read the data in. These are kind of 3 H5 files of temperature, precipitation, max, min, temperature, and precipitation. Convert them into pandas data frames. And we can look at what the data look like. So it's just a whole series of dates, latitudes, longitudes, and for example, I'm just visualizing minimum temperature here. And it's a pretty big data set, but I gave you the whole thing. So if you want to kind of explore some, this is like all the historical data from 1978 to today of temperature in the Western United States. We're going to choose just one specific random arbitrary date, July 25th, 2014, to look at temperature for. So we can look at what do the data look like for that. We have precipitation, 28, I think this is in centimeters. No, that would be too high. Millimeters of rain. Not exactly sure. That would also be too high. I think this is averaged. This is over a 2-week period, maybe. What is the precipitation starting from that date? I'll check on that. But yeah, you have precipitation data in the Western US. Combine the data sets. Okay, so let me get to the interesting stuff. So this is all just data processing. I want to project the data onto, it's kind of in lat-long coordinates. I want to project it onto a meaningful grid of meters. This is something that you have to deal with latitude and longitudinal data. Map projections. This is not very interesting, but here, this is what our data will look like. And now we can think about trying to do Gaussian process regression. And the first thing to do is to figure out what are the means of all of my variables to come up with an estimate for what the mean function should be. So my mean precipitation is 22, my mean Tmax is 30, and my mean Tmin is 15. So I'm just going to use a constant mean function, and this is very common in Gaussian processes. Constant mean function at 22 for precipitation, for example.
Hey, Genevieve, can you hear us?
I'm sorry, how much time do I have left, Caitlin? I didn't leave enough time to do this. I'm sorry.
Great if you can complete it in the next 5 minutes. So, you can just run through the collab.
Minutes.
Okay, yeah, if you could try to finish by 6:10, that'll be really great.
Okay, so I'll just go over it, but you have this notebook that you can run through. So I'm going to talk about the most important part. So the most important part of defining, this is just getting all the data in and splitting it into a train and test set. But then here we're going to define the actual Gaussian process model. So we're going to use a radial basis function or a Gaussian kernel or covariance function, which is what I talked about. And it has this is, you can play with different length scales. I talked about that length scale parameter. So here's something, a model that has a length scale 1 versus a length scale 2. And you can see that, the length scale 1 has this assumption that correlations are falling off very quickly as we move. This is, the 0 point, its 2 points are right next to each other. And then as we increase the distance between those 2 points, correlations fall off very quickly in this L equals 1 case, more slowly in the L equals 2 case. And so you can just define these GPy kernels really flexibly here. And there's also a whole library of other ones, the periodic kernel, the Matern kernel. You can do the same thing, that's a one-dimensional representation of the kernel function. We actually have 2D data, so this is a 2-dimensional representation, the same thing, like this Gaussian fall off in 2 dimensions. And then, really that's actually all you need to do to define a Gaussian process model is you define the covariance function, and then you define a GP regression model, you give it X locations, and you give it the Y observed values at those locations and a kernel function. And then you can make predictions kind of over your whole space. So for any arbitrary query point, it's forming this multivariate Gaussian finite approximation of the correlation between the points that you input and the observations that you input and the points that you're making predictions at, and using the covariance function to make estimates of the mean and the uncertainty at those prediction points. And this just talks through, how do you make predictions? How do you actually find a good length scale parameter? GPy will do that for you automatically using maximum likelihood optimization to optimize the length scale parameters of the kernel.
And then you can make warning.
That sounds great. You can make predictions that look like this. So this was the ground truth. These were the predictions that I made based on my sparse observations, and these are the errors, the scored errors in those predictions. And so you can see that even from a pretty sparse set of sensors, because these data are so smooth, you can make pretty good predictions about temperature in the rest of the country. And then the end of the tutorial is about time series data. So if instead of trying to make predictions over space, I had some, this is what temperature looks like from 1980 until today at one specific location in space. I can again train a Gaussian process model, but now I might want to use something like a periodic kernel and make predictions at a training set. And so hopefully this will take you through kind of the basics of how do you fit a GP model with real data in space and in time. And it's quite easy to do, actually. All you have to do is have a good choice of covariance function. Okay, so that's it. I mean, I hope that increased at least some practical understanding of what Gaussian process models are doing and broke down some of the barriers of how you would actually fit one or use one for your data. Any last minute questions? I think that time is up.
Okay, I think we can entertain one question.
Do you have any favorite resources you found for getting further into GPs, favorite books? The Weichel book I heard is good. I don't know if any advice.
Carl Rasmussen. It's called Gaussian Processes for Machine Learning. It's a really great it's a free book that's available online. And I would say people think of it as kind of the canonical Gaussian process reference. And he has some good examples and walks through some things. I think Gaussian processes are popular enough that there's some good Medium articles on them too, which can sometimes be more approachable than textbooks. But this is a pretty approachable textbook. It's a really good reference.
Great, thank you, Genevieve. Okay. So we'll have a very short stage break of 5 or 4 minutes from now. And the next part we have in the program is collaborathon. And it's one of the most important parts of CompSust DC because it's the part where you talk to other researchers and possibly set up a collaboration plan. And this is what leads to, 1 year-long collaboration when we